Humanity has always struggled with the question of what reality truly is. For thousands of years, we assumed the world around us was solid, fixed, and objective. The earth beneath our feet, the stars above, the passage of time itself. All of these felt so permanent that questioning their authenticity seemed unnecessary. Yet as philosophy deepened and science advanced, cracks appeared in this certainty. Ancient thinkers wondered if existence was no more than a shadow play, a projection of something greater beyond our senses. Centuries later, with the birth of modern physics, those questions returned with even greater force. At the heart of this mystery lies a possibility that both fascinates and unsettles, that our universe is not the final layer of truth, but a carefully constructed system, an immense and precise simulation. This idea is not confined to the pages of science fiction. It has found its way into mainstream scientific debate, into philosophy classrooms, into the conversations of technologists and researchers alike. The suggestion is simple, yet staggering. What if everything we know, every moment, every object, every memory, is no more than information processed by a vast, unseen system? The theory grows even stranger when combined with what we know about the quantum world. At scales smaller than atoms, matter does not behave in ways we can easily predict or understand. Particles exist in multiple states at once. Probabilities replace certainties, and observation itself appears to determine reality. This is not just difficult to imagine. It overturns the very foundation of how we think the universe should behave. And when we bring consciousness into the equation, the awareness we each carry that allows us to observe, think, and reflect, the picture becomes even more complex. Could consciousness itself be a fundamental part of this hidden system? Could our awareness be the very mechanism that brings a simulated universe into focus? This journey is not about arriving at quick answers. It is about exploring a theory that sits at the edge of science, philosophy, and imagination. The theory of the quantum mind, tied to the possibility that we live inside a cosmic simulation, asks us to reconsider everything we believe about reality, from the smallest particles to the largest galaxies, from the thoughts inside our heads to the mathematics describing them. Every piece of existence might be part of a design beyond our comprehension. Chapter 1. The question of reality. To understand the possibility of a simulated cosmos, we first need to examine the foundation of what we call reality. When you wake in the morning and see sunlight streaming through your window, it feels self-evident that the sun is there, shining across a sky that exists whether or not you are looking at it. When you touch the surface of a table, the firmness beneath your hand convinces you that matter is real, that objects are solid, and that they persist independent of your awareness. For most of human history, this assumption was taken as fact. Reality was considered external, objective, and entirely separate from the human mind. Yet there is a subtle problem here. Everything we know about the world comes to us through perception. The sunlight enters our eyes. The texture of the table is transmitted through nerves in our skin. The sound of a bird outside reaches us through vibrations carried by air. Our brains translate these signals into experiences, and it is these experiences we call reality. But can we be absolutely sure that what we perceive is the same as what exists? Could our minds be constructing a convincing representation rather than revealing the universe as it truly is? This line of thought has been central to philosophy for centuries. Plato suggested that we live in a world of shadows, reflections of a higher realm of truth. Descartes doubted whether anything could be known with certainty beyond the fact that he was thinking. More recently, philosophers have entertained the possibility that we exist inside a simulation designed by advanced beings or even by our own descendants. These ideas may sound abstract, but they strike at the heart of a profound issue. Reality is never encountered directly. It is always filtered, interpreted, and shaped by consciousness. Science too has begun to reveal that our common sense notion of reality may not hold. At the quantum scale, the smallest building blocks of matter behave in ways that defy intuition. They do not exist in one place until they are observed. They can remain in multiple states at once, only settling into a definite outcome when measured. This suggests that observation itself, and therefore consciousness, plays a direct role in shaping what we experience as real. If reality requires an observer to come into being, then perhaps it is not a fixed objective system at all. Perhaps it is participatory, unfolding through the act of perception. The question then becomes larger than science alone. If the universe is dependent on consciousness, could it be that we are living inside something designed to interact with our awareness? A simulation, by definition, is a system created to produce experiences for an observer. If the world behaves like a simulation, if matter emerges only when observed, if the rules are perfectly described by mathematical patterns, then the idea that we are inside a constructed reality begins to make sense. To ask what reality is may seem overwhelming, but it is the first step toward understanding the possibility of a cosmic simulation. The assumption that reality is simply out there waiting for us to discover may be wrong. Instead, reality could be a dynamic, interactive process shaped by both the rules of physics and the minds that perceive it. And if that is true, then the universe may be far stranger and more mysterious than we ever imagined. Chapter 2. The Dawn of Quantum Weirdness. At the beginning of the 20th century, science reached a turning point unlike anything before. For centuries, physics had been the proud foundation of certainty. Newton's laws had given us the confidence to describe falling objects, planetary orbits, and the mechanics of machines with clarity. The world seemed to run like a clock, predictable, orderly, and governed by unchanging rules. But as researchers began looking closer, examining the smallest pieces of matter, that clockwork certainty dissolved. The deeper they peered into the atom, the stranger the universe appeared, and what they found became known as quantum mechanics. Quantum mechanics did not arrive fully formed. It began with unsettling observations that classical physics could not explain. Light, for example, had always been thought of as a wave, yet experiments revealed that light sometimes behaved like particles, as though energy came in packets. These packets, later called photons, challenged the idea of smooth, continuous energy. Soon after, electrons, protons, and neutrons, the building blocks of matter, revealed behaviors that resisted every attempt at simple explanation. Instead of existing in one place or moving in a predictable path, they occupied a realm of probabilities, like shadows of possibilities overlapping one another. One of the most extraordinary features discovered was superposition. In the quantum world, particles do not settle into a single state until they are measured. An electron could be spinning up and spinning down at the same time. A photon could pass through two different paths simultaneously. It is not that we simply lack the information to know which state it is in. The reality is that the particle exists in both states at once until observation forces a choice. This idea turned centuries of scientific understanding on its head. Reality, at its smallest scale, was not fixed but fluid, not definite but potential. Another equally puzzling aspect was uncertainty. Werner Heisenberg articulated the principle that one cannot know both the position and momentum of a particle at the same time with perfect accuracy. The more precisely one quantity is known, the less precisely the other can be determined. This was not a limitation of instruments or technology. It was a fundamental feature of nature. Reality itself seemed built upon a foundation of indeterminacy, as though the universe resisted being pinned down. Then came the role of observation. Experiments such as the double-slit test showed that particles like electrons behave like waves when not observed, spreading out and interfering with one another. But when scientists placed detectors to measure which path the particle took, the wave pattern collapsed, and the particle acted like a solid, localized object. The act of observation transformed the outcome. What was once a haze of probabilities became a single definite reality only when someone or something looked. This revelation struck at the heart of how humans perceive the world. If reality depends on observation, then matter is not the bedrock we believed it to be. Instead, it is something like a canvas of probabilities that crystallize into form only under the gaze of awareness. The observer effect suggested that consciousness plays a role far deeper than previously imagined. No longer could scientists claim to be passive witnesses of an objective universe. Their presence, their choice to measure, seemed to be woven into the very structure of existence. As these discoveries unfolded, the language of physics became filled with paradoxes. Particles could be in two places at once, only to choose one when observed. Energy moved in discrete packets, jumping between levels rather than flowing continuously. The vacuum of space, once thought empty, shimmered with fluctuations of energy that never completely vanish. The deeper researchers explored, the more reality seemed to behave like something designed, like a system operating according to rules both precise and mysterious. The birth of quantum mechanics was not simply a change in theory. It was a revolution in how humanity understood the universe. Classical physics had described a world of solidity, certainty, and separation. Quantum physics revealed a world of possibility, uncertainty, and interconnectedness. Where once we imagined atoms as miniature solar systems with electrons circling like planets, we now saw them as clouds of probability, existing in many states until forced to decide. For the scientific community, these ideas were uncomfortable. Albert Einstein famously resisted the notion that the universe was governed by chance. He argued that God does not play dice with the universe. Yet the evidence continued to pile up. The mathematics of quantum mechanics worked flawlessly, predicting experimental results with incredible accuracy. Even if the picture it painted seemed bizarre, it matched the reality we observed. As strange as it all seemed, these discoveries laid the groundwork for technologies we now rely on every day. Quantum mechanics is the reason semiconductors work, enabling computers and smartphones. It explains lasers, magnetic resonance imaging, and the behavior of materials at the smallest scale. The practical success of quantum theory only underscored the unsettling truth. The universe at its foundation does not behave like the world we see, and so a new era of thought began. Reality was no longer seen as a rigid machine, but as a dynamic system shaped by possibility, uncertainty, and observation. The quantum world hinted that beneath the surface of matter lay something even more profound, a kind of informational structure that determined how reality would unfold. Some scientists began to wonder whether this informational foundation might resemble a code, something akin to the instructions in a simulation. If the smallest pieces of matter behave as though they wait for observation before becoming real, what does that suggest about the nature of the universe itself? Quantum mechanics gave us the first glimpse into a reality stranger than imagination. It revealed a universe that resists simplification, a universe where certainty gives way to probability, where matter exists in superpositions until awareness calls it forth. It is within this strangeness that the seeds of the simulation hypothesis took root, for a world so dependent on observation and information begins to look less like an independent reality and more like an interactive system. The dawn of quantum weirdness was not simply the birth of a new science. It was the first clue that reality may not be what it seems. Chapter 3. Consciousness and the Observer Effect. Few experiments in the history of science have shaken our understanding of the universe as deeply as the double-slit experiment. At first glance, it appears simple. Fire tiny particles like electrons or photons at a barrier with two narrow slits, and observe what appears on a screen placed behind it. If only one slit is open, the particles create a single band on the screen, as one would expect from small objects moving through space. But when both slits are open, something far stranger happens. Instead of two bands, a wave-like interference pattern appears, as though each particle passed through both slits simultaneously, interfering with itself like ripples of water overlapping in a pond. This result was baffling. The experiment suggested that particles are not solid, localized entities traveling along a single path, but rather probability waves, existing in multiple states at once. The electron is not here or there, but both here and there, until something forces it to decide. Reality, at this scale, seemed less like a definite structure and more like a canvas of possibilities. But the true shock came when scientists attempted to measure which slit the particle actually passed through. Detectors were placed at the slits to record the particle's path. The moment observation entered the equation, the interference pattern vanished. Instead of behaving like waves, the particles behaved like discrete objects, producing two distinct bands, as if each particle had chosen a single slit. The simple act of observing collapsed the wave of possibilities into a single outcome. This phenomenon became known as the observer effect, and it continues to provoke deep questions about the relationship between consciousness and reality. Why should the act of measurement of observation alter the outcome of an experiment? If the universe exists independently of us, then particles should not care whether or not we are watching. Yet the evidence shows otherwise. Without observation, the world exists in probabilities. With observation, those probabilities collapse into concrete reality. The implications are staggering. It suggests that consciousness, or at least the act of measuring, is not separate from the physical universe, but is directly involved in shaping it. In the everyday world, we do not notice this because the sheer number of interactions averages out into stable, predictable patterns. But at the quantum level, where probabilities rule, the influence of observation becomes undeniable. This connection between observer and observed has led to countless debates. Some physicists argue that consciousness is not required, that the interaction with any measuring device is enough to collapse the wave function. Others, however, see something more profound. If reality does not crystallize until it is observed, then perhaps awareness itself is fundamental to the universe. Our minds may not be passive witnesses, but active participants, bringing reality into existence. The philosopher Eugene Wigner, a Nobel Prize-winning physicist, suggested that consciousness is essential to the quantum process. He argued that without conscious observation, the collapse of the wave function could not occur. In his view, the universe as we know it depends on the presence of aware minds to manifest definite outcomes. This interpretation transforms consciousness from an accidental byproduct of brain activity into a cornerstone of reality itself. To grasp the weight of this idea, consider what it means in daily life. Every object you see, every sound you hear, every sensation you feel exists for you only because your awareness renders it real. If no mind ever looked upon the moon, would it exist in the same way? Would it be a solid object circling Earth, or merely a haze of probabilities waiting for consciousness to bring it into clarity? The observer effect suggests that the very act of noticing, of being aware, breathes existence into the universe. The unsettling suggestion here is that reality is not entirely independent of us. Rather than being a stage upon which we act, it is a dynamic system shaped through interaction with consciousness. This challenges the classical view of a universe indifferent to observers. Instead, it implies a participatory cosmos where mind and matter are inseparably linked. Some interpretations of quantum mechanics, such as the Copenhagen interpretation, embrace this strange role of observation. Others, like the many worlds interpretation, avoid it by suggesting that all possibilities exist simultaneously, and observation merely determines which branch of reality we experience. Yet even in these alternative views, the connection between measurement and reality remains central. The double-slit experiment forces us to confront the possibility that reality is incomplete without observation. This intersection of consciousness and physics lays the foundation for the theory of the quantum mind. If awareness has the power to shape outcomes at the smallest scale, then perhaps consciousness itself is not confined to the brain, but is woven into the very fabric of the cosmos. Our minds may be quantum participants in a universe that requires them, not passive reflections of physical processes, but co-creators of reality. The observer effect is more than a curious anomaly in physics. It is a clue, a doorway into a deeper mystery. It hints that the universe may not be the solid, objective realm we once believed. Instead, it may be a simulation-like process, unfolding probabilities into experiences through the lens of awareness. This possibility reframes not only science, but philosophy, suggesting that consciousness and reality are two sides of the same coin. The double-slit experiment remains one of the most profound scientific demonstrations of this principle. It shows that the universe is not complete without observation, that probability collapses into certainty through the act of awareness. In this sense, consciousness does not merely witness reality, it helps to create it. Chapter 4. The birth of the simulation hypothesis. Long before the term simulation entered the scientific lexicon, human beings wrestled with the possibility that reality might not be what it appears. Philosophers, mystics, and scientists alike have questioned whether the world we inhabit is the ultimate ground of being, or merely a projection, an imitation of something deeper. This line of inquiry stretches back thousands of years, with its earliest seeds found in the reflections of ancient thinkers. One of the most enduring metaphors for this suspicion comes from the Greek philosopher Plato. In his famous allegory of the cave, he imagined prisoners chained in darkness, facing a blank wall. Behind them burns a fire, and between the fire and the prisoners pass people carrying objects, casting shadows on the wall. The captives, knowing nothing else, mistake these shadows for reality. Only by breaking free and stepping into the light outside can they realize that what they had taken as the entirety of existence was only a faint projection. Plato's allegory was not merely a story about illusion. It was a challenge to question whether the reality we perceive is the full truth or a limited version, constrained by our senses and our perspective. This idea echoed across centuries. Eastern traditions, such as Hinduism, describe the world as Maya, an illusion or veil obscuring a deeper, truer reality. Mystical traditions across cultures suggested that the universe we experience is more akin to a dream than to an unchanging, solid truth. Though these ideas arose from spiritual insight rather than empirical science, they planted the seed of doubt that what appears as real might not be absolute. Fast forward to the modern era, and advances in technology began to give new form to these age-old suspicions. With the rise of digital computing in the 20th century, humanity gained the ability to create virtual worlds, at first crude and pixelated, then increasingly sophisticated. The development of video games, virtual reality, and computer simulations demonstrated that entire environments, characters, and histories could be generated through code. For the first time, we could see directly how complex, immersive realities could exist inside machines, raising a provocative question. If we can build such worlds, could we ourselves be living in one? This speculation found rigorous framing in the work of philosopher Nick Bostrom in the early 2000s. In his seminal paper, he laid out the simulation argument, which does not claim outright that we live in a simulation, but rather that one of three possibilities must be true. The first is that civilizations like ours almost never reach the level of technological maturity required to run highly detailed ancestor simulations. The second is that advanced civilizations, even if they do reach such a stage, would have no interest in running such simulations. The third is that if advanced civilizations do run such simulations, then the number of simulated realities would vastly outnumber the single base reality, making it statistically more likely that we are inhabitants of one of those simulations rather than the original universe. Bostrom's argument gained immediate traction because of its logical structure. Unlike science fiction scenarios, it did not require extravagant assumptions about alien gods or magical machinery. It relied instead on clear reasoning about probabilities and technological progress. If computation continues to grow more powerful, and if curiosity about our past is as strong in advanced civilizations as it is in ours, then simulated realities could proliferate. In that case, what reason do we have to believe we are in the original reality, rather than one of countless imitations? This hypothesis dovetails with quantum puzzles, particularly the observer effect and the probabilistic nature of particles. If reality is fundamentally digital or computational, then the strangeness of quantum mechanics could be explained as a kind of rendering system. Just as a video game only renders the parts of the world that the player sees, perhaps the universe only collapses probabilities into definite outcomes when observed. In this way, the observer effect could be understood not as an inexplicable quirk of physics, but as evidence of a deeper architecture. The simulation hypothesis also resonates with cultural narratives that preceded it. Plato's cave, the idea of Maya, and centuries of philosophical skepticism all hinted at a hidden structure behind appearances. What Bostrom offered was a framework that united those intuitions with the technological realities of the modern age. Computers showed us that worlds can be generated. Mathematics and logic suggested that if it is possible to generate simulated universes, then it becomes nearly impossible to rule out the possibility that ours is one of them. Yet the idea does not stop with philosophy. Leading figures in science and technology have publicly entertained the notion. Elon Musk, for example, has stated that he believes the odds we are in base reality are extremely small. Physicists like Neil deGrasse Tyson have admitted that the simulation hypothesis cannot be dismissed outright. While not universally accepted, it has entered serious discussions across disciplines, not as an eccentric fantasy, but as a hypothesis that sits at the intersection of philosophy, physics, and computer science. The birth of the simulation hypothesis thus represents a convergence. Ancient philosophy questioned the reliability of perception. Mystical traditions warned of illusion. Modern technology provided a concrete demonstration of artificial worlds, and contemporary philosophy distilled these threads into a structured argument. Together, they form a powerful narrative that the universe may not be the bottom layer of reality, but instead a construction, a simulation unfolding within a deeper framework we cannot directly access. If this is true, the implications reach far beyond science. It challenges notions of free will, meaning, and the nature of consciousness itself. Are our choices authentic? Or are they the outputs of code written by unseen programmers? Is consciousness an emergent property of physical processes? Or is it the defining feature of reality that even simulations cannot erase? These questions lie at the heart of the theory we are exploring. The simulation hypothesis is not just a thought experiment. It is a lens that reshapes how we view every mystery, from quantum physics to human experience. It does not provide definitive answers, but it forces us to reconsider the assumptions that underlie our sense of reality. To trace its birth is to recognize that humanity has long suspected the world we see is not the ultimate truth. What is new is that we now possess the intellectual and technological tools to seriously entertain that suspicion, turning myth and allegory into hypothesis and argument. Chapter 5. Information as the foundation of the universe. The further we peer into the workings of nature, the more we encounter a reality that resists our old definitions of matter and energy. For centuries, the universe was understood as a collection of objects. Planets, rocks, atoms, and particles all moving under physical laws. But as physics advanced into the quantum and cosmological realms, that picture began to fracture. Instead of concrete objects, we found patterns, probabilities, and mathematical relationships. This shift led to a profound idea, championed by physicist John Archibald Wheeler, that at the most fundamental level, reality is not built from matter at all, but from information. He summarized this idea with a striking phrase, "it from bit." Wheeler proposed that every physical entity, every it, arises from binary choices, or bits. In this vision, the universe is not a giant machine made of particles, but a vast informational system, more like a computational process. Instead of matter being the foundation upon which everything else rests, information is the true substrate, and what we call matter is simply the emergent pattern of encoded data. This concept transforms how we think about existence. If it from bit is correct, then reality is not a solid stage upon which events unfold, but an ongoing act of information processing. The electron's properties, the photon's behavior, the fabric of space-time itself, all can be understood as manifestations of informational states. When an observation is made, it is not a particle deciding where to be, but the universe updating its informational record. In this light, the observer effect takes on a new dimension. Observation is not merely collapsing probabilities, but registering a new bit of information, locking it into the unfolding program of the cosmos. Evidence for this view emerges from many corners of science. Quantum mechanics already suggests that particles have no definite state until measured. In informational terms, this can be seen as the system conserving resources, only finalizing details when required. This mirrors how video games operate, rendering only the parts of the environment that the player encounters. In a similar way, the universe may be economizing its informational load, updating reality through interactions and observations. Cosmology also provides hints. Black holes, once thought to be cosmic vacuum cleaners swallowing matter forever, are now understood as storing information about everything that falls into them. Stephen Hawking's work on black hole radiation revealed a paradox. If information were destroyed inside black holes, fundamental laws of physics would collapse. Later research suggested that black holes do not erase information, but encode it on their surfaces, leading to the bold claim that the universe itself may operate like a hologram. Every event, every particle, every configuration is recorded as data, preserved at the boundaries of reality. This holographic principle aligns perfectly with Wheeler's it from bit. If the universe is fundamentally informational, then matter and energy are not the bedrock, but the output of processing rules. Physical laws themselves can be viewed as algorithms, consistent patterns of updating data across the cosmos. Gravity, electromagnetism, and nuclear forces may all be expressions of deeper informational logic, like rules in a simulation. The implications are staggering. If reality is built on information, then it becomes indistinguishable from a computation. What we experience as physical solidity is simply the emergent product of underlying code. Atoms are data clusters. Forces are rules of interaction. Space and time themselves may be derived coordinates in an informational grid. In this light, the simulation hypothesis gains credibility because what we already observe looks eerily like the structure of a programmed reality. Even consciousness itself begins to fit within this framework. If the brain is not merely a biological machine but an informational processor, then thought, perception, and awareness can be understood as high-level expressions of data manipulation. Our sense of self, our memories, our decisions are all informational flows in a system that may be computational at its deepest level. Far from diminishing consciousness, this elevates it, because it suggests that the very act of experiencing is part of the informational fabric that keeps reality coherent. What makes Wheeler's vision powerful is its simplicity. At base, the world reduces to binary outcomes. Yes or no, up or down, 1 or 0. Every event is a registration of information, a fundamental choice etched into the history of the universe. This framework not only explains the quantum world's quirks, but also unifies them with the digital age we now inhabit. Our computers, after all, operate on bits, and they are capable of generating vast, convincing realities. It may not be a coincidence that the same logic underlies both our machines and the cosmos itself. If information is primary, then the universe is not a chaotic accident, but a structured flow of encoded meaning. This opens doors to profound philosophical questions. Who or what established the informational rules? Are we participants in an ongoing computation? Or is this processing self-sustaining, an eternal cycle of data unfolding? Could the constants of physics be the equivalent of code settings, fine-tuned in ways that allow life and awareness to emerge? These questions do not admit easy answers, but they illustrate how the informational view reshapes every corner of science and philosophy. The transition from matter to information represents one of the most radical shifts in human thought. It challenges the deepest assumptions about what is real. We once believed the universe was a collection of objects. Now we are coming to see it as a tapestry of data, woven by rules that resemble computation. Wheeler's phrase, "it from bit," captures this revolution in 3 short words, hinting that everything we experience, every star, every thought, every particle, is the manifestation of information at work. Chapter 6, The Quantum Mind Theory. Among the deepest puzzles of human existence is the question of consciousness. What is it that makes us aware, able to feel, to think, to experience the world, rather than simply process it mechanically? Classical neuroscience explains much about the brain's wiring, synapses, and chemistry, but it struggles with the so-called hard problem of consciousness. How does subjective experience arise from electrical and chemical signals? This gap between physical processes and conscious awareness has led some researchers to suspect that the answer lies not in classical physics, but in the strange, non-intuitive world of quantum mechanics. 2 of the most prominent figures to advance this line of thinking are mathematician Roger Penrose and anesthesiologist Stuart Hameroff. Together, they developed what is known as the ORC-OR model, short for orchestrated objective reduction. Their proposal is as bold as it is controversial. Consciousness arises from quantum computations occurring inside the brain's neurons, specifically within tiny structures called microtubules. Penrose's journey into this theory began with his exploration of the limits of computation. He argued that human understanding, especially in mathematics, cannot be fully explained by algorithms. There seems to be an element of insight, an ability to grasp truths that no step-by-step procedure can account for. From this observation, Penrose concluded that the mind must operate in ways that go beyond classical computation, hinting at a deeper process rooted in the physics of reality itself. Hameroff, coming from a medical background, was fascinated by the complexity of microtubules' cylindrical protein structures inside neurons that act as scaffolding and pathways for cellular functions. He proposed that these microtubules could be more than structural components. They could be the very sites where quantum processes take place. If these structures are capable of maintaining quantum coherence, something once thought impossible in the warm, wet environment of the brain, then they could serve as the hardware for a kind of quantum computation. Together, Penrose and Hameroff merged their insights into ORC-OR. The orchestrated part refers to the way biological processes might guide and stabilize quantum activity in microtubules, while objective reduction refers to Penrose's idea that quantum states collapse not randomly, but according to an underlying principle tied to the fabric of space-time. In their model, Moments of conscious awareness correspond to these orchestrated collapses of quantum states inside neurons. Each collapse is like a frame in the film of consciousness, producing the flow of subjective experience. What makes this theory striking is how it bridges physics and mind. Instead of viewing consciousness as a byproduct of neural circuits, it treats awareness as a quantum phenomenon, deeply connected to the structure of the universe. If true, this would mean that consciousness is not just an emergent property of the brain, but a fundamental process intertwined with reality itself. In this sense, the mind is not separate from the cosmos, but an expression of its quantum fabric. The Orc-Or theory also provides a fresh perspective on questions that classical neuroscience struggles with. For example, how can billions of neurons firing in parallel produce a unified sense of self, rather than a cacophony of disconnected experiences? Quantum coherence allows for states to be linked across distances, producing a holistic unity. If microtubules within neurons maintain quantum entanglement, then consciousness could arise as an integrated whole, rather than as scattered fragments of activity. Critics, of course, have raised objections. Maintaining quantum states in biological systems is notoriously difficult, as decoherence usually destroys delicate quantum effects. Yet research in quantum biology has shown that certain processes, such as photosynthesis and bird navigation, may indeed rely on quantum phenomena. If plants and animals can exploit quantum mechanics, it is not unreasonable to suspect that the brain might as well. Recent studies have even suggested that microtubules display behaviors consistent with quantum vibrations, lending support to Hameroff's early intuition. If the Orc-Or model holds weight, the implications extend beyond neuroscience. It suggests that consciousness is not an accidental feature of evolution, but a fundamental phenomenon connected to the deep structure of reality. This aligns with broader questions in physics and philosophy, such as whether the universe itself is conscious in some way, or whether our minds tap into a larger informational field. The quantum mind theory transforms consciousness from a private mystery into a cosmic principle. Moreover, if our awareness emerges from quantum processes, it strengthens the case for the simulation hypothesis. Quantum computation is already recognized as vastly more powerful than classical computation. If the brain itself is a kind of natural quantum computer, then consciousness could be seen as a product of high-level quantum programming. This would mean that if we are living in a simulation, our consciousness might not be an illusion, but a feature deliberately encoded into the system, perhaps even necessary for the simulation to function. The Orc-Or model, whether ultimately proven or not, challenges us to rethink the boundary between physics and mind. It refuses to reduce consciousness to neural machinery and insists that awareness belongs in the same conversation as quantum theory, gravity, and cosmology. In this view, to study the mind is to study the universe itself, because the two are not separate. They are deeply interwoven, connected through the informational and quantum foundations of existence. The quantum mind theory does not simply ask how the brain works. It asks why reality is structured in such a way that awareness can arise at all. It suggests that consciousness is not a latecomer in the story of the cosmos, but a central element woven into its very design. And if that is true, then our experience of the world may be more than a fleeting biological accident. It may be the very purpose of the cosmic simulation we are questioning. Chapter 7. Brains as Quantum Computers. The human brain is often described as the most complex structure known in the universe. With nearly 86 billion neurons and trillions of connections, it operates with a sophistication that outstrips even our most advanced supercomputers. Yet despite decades of research, the precise mechanisms underlying thought and consciousness remain elusive. One compelling possibility is that the brain functions not merely as a classical processor, like the silicon machines we build, but as a biological quantum computer, A classical computer manipulates bits, ones and zeros through predictable circuits. A quantum computer, by contrast, leverages quantum bits, or qubits, which can exist in superposition, representing both 0 and 1 simultaneously. This property allows quantum systems to process vast amounts of information in parallel, performing calculations that classical systems would find impossible in practical timeframes. If the brain exploits similar principles, it could explain its extraordinary capabilities, intuition, creativity, and the seamless integration of sensory input into a unified conscious experience. The architecture for such a system may lie within the neuron itself. Microtubules, the protein structures inside cells, provide an intricate lattice where quantum phenomena could occur. Their cylindrical arrangement and electrical properties suggest they might sustain coherent quantum states, acting as qubits in a biological processor. When scaled up across billions of neurons, these quantum processes could interconnect, enabling the brain to perform computations far beyond the reach of conventional physics. One of the key features of quantum computation is entanglement, where particles become linked in such a way that their states are correlated no matter how far apart they are. If the brain's microtubules utilize entanglement, this could offer an explanation for the unity of consciousness. Instead of individual neurons firing independently, the brain could be coordinating vast networks of activity instantaneously, weaving together perception, memory, and awareness into a single coherent field of experience. This perspective reframes the brain not just as a machine of flesh, but as a quantum interface with the universe itself. By processing information at the quantum level, consciousness may directly tap into the foundational fabric of reality. Instead of being confined within the skull, awareness could be entangled with the broader cosmos, part of an informational web that extends beyond the individual. This would explain why consciousness feels both intensely personal and yet mysteriously universal, as if it participates in something larger than the self. Research in quantum biology has begun to uncover how life itself exploits quantum effects. In photosynthesis, plants use quantum coherence to transfer energy with near-perfect efficiency. Birds navigate using entangled particles sensitive to Earth's magnetic field. Enzymes catalyze reactions by tunneling through energy barriers that classical physics cannot explain. These discoveries demonstrate that biology is not limited to classical mechanics. It is capable of harnessing quantum principles in functional, reliable ways. If these mechanisms are present in plants, birds, and enzymes, why not in the human brain? Considering the brain as a quantum computer also provides insights into phenomena that defy classical explanation. Take, for example, the speed and fluidity of human thought. Neurons operate relatively slowly compared to electronic circuits, firing only a few hundred times per second. Yet the brain outperforms classical supercomputers in tasks involving pattern recognition, creativity, and problem-solving. If neurons are leveraging quantum superposition and entanglement, they would gain exponential computational power, solving problems by exploring countless possibilities simultaneously and converging on solutions in ways classical systems cannot. Dreams, intuition, and sudden flashes of insight may also find explanation within this framework. These experiences often feel as though they arise from beyond linear, step-by-step reasoning. A quantum brain could explore vast informational landscapes at once, presenting the conscious mind with solutions that appear spontaneously, as if delivered from nowhere. In truth, they may be the result of quantum processes unfolding beneath the surface of awareness. The implications extend into the realm of the simulation hypothesis. If our brains are quantum computers, then consciousness may serve as both a participant in and a decoder of the simulation. Just as a quantum computer processes information at levels inaccessible to classical machines, human awareness may be designed to interface with the deepest layers of the informational architecture of reality. Rather than being accidental observers in a meaningless universe, we could be quantum participants in a coded cosmos. Critics argue that sustaining quantum states in the warm, wet environment of the brain is implausible, as decoherence usually disrupts delicate quantum effects. Yet, ongoing studies suggest that biological systems have developed mechanisms to shield and sustain coherence. The very structure of microtubules may provide such protection, with their ordered geometry stabilizing quantum states long enough for meaningful processing to occur. What once seemed impossible in principle may turn out to be a feature of biology's ingenuity. If brains truly function as quantum computers, then consciousness is not confined to the boundaries of classical matter. It is an active engagement with the quantum fabric of existence. This transforms our understanding of life and mind. We are not isolated individuals trapped in bodies, but quantum beings interconnected with the deeper layers of reality. Awareness, in this sense, is a bridge between the biological and the cosmic, between the simulation and the simulated. The theory that brains are quantum computers does more than explain the mysteries of cognition. It offers a vision of humanity's place in the universe. Consciousness becomes not an accidental byproduct of evolution, but a profound capacity to resonate with the quantum architecture of existence. By understanding the brain this way, we begin to glimpse how mind and cosmos mirror one another, each shaped by the same informational principles. Chapter 8: Entanglement and the Web of Connection. Among the many mysteries that quantum physics has revealed, few are as baffling and unsettling as entanglement. At its core, entanglement occurs when two or more particles interact in such a way that their states become linked, no matter how far apart they later drift. When one particle is measured, its twin instantly reflects the result, as if information travels between them faster than light. To Einstein, this was so strange that he dismissed it as spooky action at a distance. Yet decades of experiments have confirmed that entanglement is not an illusion. It is real, repeatable, and deeply woven into the structure of reality. To appreciate the significance of entanglement, imagine preparing two photons so that they share a quantum state. You then separate them by vast distances, perhaps placing one on Earth and sending the other toward a spacecraft millions of miles away. If you measure the polarization of the photon on Earth, the other photon instantly adopts the corresponding complementary state, regardless of the separation. The effect happens without any detectable signal passing between them. This suggests that the connection is not mediated through space and time, as we normally understand it. Instead, entangled particles share a deeper unity that transcends spatial distance. Physicists have tested entanglement rigorously through experiments known as Bell tests. These experiments demonstrate that the correlations between entangled particles cannot be explained by hidden variables or classical mechanisms. The results violate Bell's inequalities, showing that quantum mechanics cannot be reduced to a deterministic picture of pre-existing properties. The universe, at its core, behaves in ways that defy the expectations of classical logic. Entanglement is not a quirk or side effect. It is a fundamental feature of reality. The implications are staggering. If entanglement extends beyond the laboratory, it suggests that everything in the universe may be interconnected. Since all particles were once part of the same singularity before the Big Bang, the possibility arises that remnants of entanglement still thread through the cosmos. What we perceive as separate objects and beings might in truth be fragments of a single unified quantum state. The boundaries that appear so rigid between you and me, between one star and another, may be illusions created by our limited perception. This web of connection challenges our assumptions about individuality and separateness. Consciousness itself could be entangled, not confined within isolated skulls, but participating in a greater field of awareness. If the brain, as discussed previously, operates as a quantum processor, then its activity may resonate with entangled networks that extend beyond the body. Awareness might not simply arise within individuals, but could be shared, distributed, or linked in ways we cannot yet fully grasp. Entanglement also reframes the simulation hypothesis. If reality is a coded system, entanglement may represent the architecture's way of maintaining coherence across its network. In computer science, distributed systems must ensure that data remains synchronized across distant nodes. Entanglement could be the universe's equivalent of this synchronization, enforcing consistency within the simulation. When two entangled particles instantly align their states, it may be the underlying code updating itself to preserve the integrity of the system. This perspective transforms the eerie phenomenon into something almost familiar. Just as a video game engine ensures that objects maintain continuity across a rendered world, the universe's informational substrate may employ entanglement to synchronize reality across space and time. Rather than defying logic, entanglement may be the most direct evidence that reality operates like a computational system. Still, entanglement resists easy explanation. It violates our sense of causality, undermines locality, and suggests a deeper order we cannot directly see. Some physicists propose that space and time themselves are emergent properties built upon entanglement. In this view, the geometry of the universe arises not from particles moving in pre-existing space, but from networks of entangled states. Space is not the stage where physics unfolds. It is the illusion created by the web of entanglement itself. This idea echoes ancient philosophical traditions that envisioned reality as an interconnected whole. Mystics across cultures have spoken of oneness, the interconnectedness of all beings, and the illusion of separateness. Quantum entanglement offers a scientific parallel, grounding those intuitions in empirical evidence. It shows us that beneath the apparent fragmentation of the world lies a hidden unity that transcends distance and time. What does this mean for human experience? If everything is entangled, then our actions ripple outward in ways far beyond our immediate surroundings. Consciousness, too, may participate in this quantum web, with thoughts and intentions influencing reality, not through crude physical force, but through resonance with deeper informational structures. While speculative, this possibility encourages us to reconsider the scope of human agency and responsibility. Entanglement also opens new pathways for technology. Quantum communication, based on entangled particles, promises secure transmissions that cannot be intercepted without detection. Quantum networks could connect computers across the globe in ways far faster and more powerful than classical systems allow. These innovations hint at a future where humanity not only theorizes about entanglement, but learns to harness it, weaving ourselves more deliberately into the quantum fabric of reality. At its heart, entanglement forces us to confront the fact that our familiar categories, separateness, distance, independence, may be illusions. The cosmos is not a collection of isolated parts, but a seamless whole, a tapestry woven from threads that remain invisible until tested. When we peer deeply enough, we find not disconnection, but unity. That unity may be the key to understanding both consciousness and the simulation-like qualities of existence. Chapter 9. The Illusion of Time and Space. For centuries, human beings have taken time and space as the unquestioned foundations of reality. We grow up sensing the passage of seconds, minutes, and years. We navigate through 3 dimensions of space, as though they form the unshakable stage on which life unfolds. Einstein's theory of relativity deepened this understanding, showing that time and space are intertwined into a single continuum, bending under the influence of gravity. Yet even Einstein considered this fabric as real, an objective framework within which the drama of the cosmos takes place. Quantum physics, however, has pushed us toward a far more radical idea. What if time and space themselves are not fundamental? What if they are emergent illusions born from something deeper? One of the first hints that space and time might be emergent comes from quantum entanglement. Experiments show that particles separated by enormous distances behave as though connected instantly, without traversing space or time. This defies the assumption that information must move across the stage of space-time at the speed of light or slower. Instead, entanglement points toward a reality where space and time do not limit interactions. They may be secondary structures, convenient illusions arising from more primitive building blocks of the universe. Physicist John Wheeler once proposed that reality might arise from bits of information, rather than from space, time, or matter. His idea, it from bit, suggests that the universe is not built on objects or fields, but on the answers to yes or no questions, the simplest units of information. If Wheeler is correct, then space and time could be the emergent scaffolding that arises when information organizes itself into consistent patterns. In this way, the flow of time and the extension of space are byproducts of deeper informational processes. The holographic principle adds further weight to this possibility. Proposed by Gerard 't Hooft and Leonard Susskind, it suggests that the information describing a region of space can be encoded on its boundary surface, much like a hologram stores a three-dimensional image on a two-dimensional film. In this framework, space and time within the region are emergent illusions generated by the information written on the boundary. Reality becomes less like a solid structure and more like a projection. Just as a hologram seems three-dimensional, but is ultimately only light encoded on a flat surface, the vast expanse of space and the relentless march of time could be the byproducts of underlying informational codes. Even more striking is the work of Juan Maldacena on the ADS-CFT correspondence, which shows mathematically that certain space-time geometries can emerge from lower dimensional quantum systems without gravity. This means that space itself can arise from quantum entanglement patterns. Time, too, may be an emergent property, an ordering imposed on quantum events, rather than a fundamental flow. When we look at the cosmos through this lens, time is not the river we drift upon, but the illusion of sequence generated by correlations between quantum states. This challenges how we perceive memory, identity, and continuity. Our sense of a past leading to a present and stretching toward a future could be a construction of consciousness interpreting correlations. Time might not exist as a universal flow, but as an emergent narrative that allows observers to make sense of events. In other words, the human mind could be a participant in shaping the illusion of time itself. Space, too, may be less solid than we imagine. Recent advances in quantum gravity suggest that the geometry of the universe, the distances between points, the curvature of space, the expansion of the cosmos, arises from entanglement. Space is not the arena in which entanglement takes place. Entanglement is the raw material out of which space is woven. Imagine a tapestry, where the threads are not laid upon a fabric, but are the fabric itself. Pull one thread, and the pattern shifts. Entanglement plays that role in constructing the spatial relationships that give us the impression of a vast external universe. If time and space are emergent, the simulation hypothesis gains even more credibility. In a digital simulation, the game world exists only as coded data. Space is rendered when the program calculates positions of objects, and time flows only because the system updates frame by frame. Within such a simulation, the characters perceive space and time as fundamental, even though they are artificial constructs. Similarly, our universe may be running on a deeper computational substrate, where space-time is not the core reality, but a projected interface like the graphics of a video game. The illusion of time also raises profound questions about free will, destiny, and the nature of change. If all events exist simultaneously in a deeper quantum reality, then the flow of time may be like flipping through frames of an already completed film. Our choices could still feel meaningful because we experience them sequentially, but on the underlying level, everything may already exist. This interpretation, sometimes called block universe theory, fits well with relativity, which treats all points in spacetime as equally real. Yet quantum physics adds another layer, suggesting that the sequence we perceive emerges from entanglement patterns rather than being written into the foundation of existence. This concept resonates with ancient traditions that spoke of time as cyclical, illusory, or dreamlike. Eastern philosophies like Hinduism and Buddhism have long described the phenomenal world as Maya, an illusion overlaying a deeper reality. Modern physics, remarkably, seems to circle back toward a similar intuition, that what we take as the most concrete aspects of experienced time and space are not ultimate truths, but veils masking a deeper structure. The idea also impacts our understanding of death and continuity. If time is emergent, then the end of personal experience may not be as final as it seems. Just as frames in a film always exist regardless of which is being projected, moments of consciousness might persist in ways that defy the linear error we experience. While speculative, this possibility stretches the imagination toward the notion that consciousness itself could transcend the apparent boundaries of time and space. If space is emergent, distance loses its ultimate meaning. The vast gulfs between stars may be projections, not fundamental separations. Connectivity, not separation, is the deeper reality. This ties back to entanglement's suggestion of unity and hints at why quantum mechanics resist localization. Reality may be one indivisible whole, and the space-time grid is a perceptual convenience rather than the ultimate truth. As physics continues to probe these questions, one message grows clearer. Time and space are not the bedrock of the cosmos. They are astonishingly convincing illusions, projections that allow complex interactions to manifest in coherent ways. Whether they emerge from quantum entanglement, informational codes, or computational substrates, the truth is that reality is deeper, stranger, and more interconnected than the surface appearance suggests. Chapter 10. Glitches in reality. When people speak of glitches in the Matrix, it often sounds like the stuff of science fiction. Yet, throughout history and into the present day, countless individuals have reported strange experiences that do not align with the normal flow of reality. These anomalies, sudden duplications, repeating events, impossible coincidences, or disruptions in the fabric of daily life bear an uncanny resemblance to the glitches we see in digital systems. While skeptics dismiss them as tricks of memory or perception, the simulation hypothesis invites us to view them differently, as potential cracks in the veneer of our constructed universe. One category of anomaly, often described as a glitch, is déjà vu. This sensation of having lived through a moment before is so common that nearly everyone has experienced it at least once. Neuroscience attributes it to memory misfires, where the brain mistakes a current perception for a recollection. But if reality is a simulation, déjà vu could be evidence of a system reloading, repeating a sequence, or mismanaging stored information. In video games, loops or errors in code sometimes cause a player to repeat a scene or action unintentionally. The eerie familiarity of déjà vu may reflect a similar hiccup within the cosmic engine. Another phenomenon often cited is synchronicity, a term popularized by psychologist Carl Jung. Synchronicities are meaningful coincidences where unrelated events align in ways that seem too precise to be chance. For example, thinking of an old friend only to receive a call from them moments later, or encountering a specific symbol repeatedly across different contexts within a single day. While randomness can explain some coincidences, the clustering of meaning behind these events points towards something deeper. In a simulation, such synchronicities could occur when the code governing probabilities subtly adjusts, bending events toward alignment without explicit cause. They resemble Easter eggs hidden in a program, intentional or otherwise. Even stranger are reports of physical anomalies, objects appearing in two places at once, time seemingly skipping, or people witnessing brief pauses in activity around them. Stories abound of individuals noticing that the world feels momentarily frozen, as though reality hesitated before continuing. In the digital world, these would be frame drops, lag spikes, or rendering errors. Within the simulation framework, they may reflect the underlying system struggling to maintain coherence under computational strain. On a larger scale, unexplained anomalies in science echo this idea. The Mandela effect, for example, refers to collective false memories, where groups of people vividly recall details that differ from the historical record. Some insist they remember the spelling of a brand, the ending of a movie, or even significant historical facts differently than they appear today. While psychologists explain this as the malleability of memory, others see it as potential evidence of system updates like patches to the simulation's code that retroactively alter reality. If the simulation changes its database, those who recall the earlier version experience cognitive dissonance, interpreting it as a memory glitch. Astrophysical mysteries may also be interpreted through this lens. The unexplained uniformity of the cosmic microwave background, the strange distribution of dark matter, or sudden, unanticipated cosmic events might not be natural occurrences but adjustments in the simulation's rendering of the cosmos. Just as a game engine updates its environment for optimization, the universe might correct or revise its structures in ways that appear inexplicable to observers bound by space and time. One of the most compelling aspects of glitches is how they capture attention. When a glitch occurs in a video game, players immediately notice because it disrupts immersion. Similarly, reality glitches stand out precisely because they jar us from the seamless flow of life. They reveal the seams in the fabric of existence, suggesting that behind the convincing facade lies a coded architecture not meant to be seen. The fact that these moments provoke such strong reactions may not be accidental. They could be design checkpoints, reminders, or tests woven into the simulation itself. Skeptics argue that these phenomena are psychological, byproducts of how the human brain processes complexity. The brain seeks patterns, often imposing meaning where none exists. Memory errors, perception biases, and statistical quirks can explain much of what people label as glitches. Yet, even if these accounts arise from the mind, one must ask, what is the mind itself? If consciousness is linked to quantum processes interacting with an underlying code, then mental errors could still represent interactions with that code. What we dismiss as psychological noise may be the very interface through which the simulation communicates. It is also worth considering whether glitches are intentional features rather than flaws. In a video game, glitches can sometimes act as shortcuts or hints, revealing hidden layers of the system. If our reality is simulated, then glitches might be deliberate artifacts, breadcrumbs left by the architects. They could function as invitations to question reality, nudging observers toward greater awareness. The uncanny unease people feel during such moments may be part of that design, a disruption intended to awaken curiosity. For those who take the simulation hypothesis seriously, glitches are not just curiosities, but evidence. They are the data points that hint at the boundaries of the system. Each unexplained anomaly becomes a clue, suggesting that reality is not what it seems. The challenge lies in distinguishing genuine glitches from ordinary errors of perception. But the pattern of these events, their recurrence across cultures and time gives them weight. Ultimately, glitches remind us of the fragility of the story we tell ourselves about the world. They expose cracks in the illusion of seamless continuity, revealing the possibility that beneath the surface lies a programmable substrate, whether intentional or accidental. They confront us with the unsettling possibility that we are not merely participants in reality, but inhabitants of a system, observed, maintained, and occasionally disrupted by processes beyond our understanding. Chapter 11. Mathematics, the language of the simulation. There is a peculiar fact about our universe that has baffled scientists and philosophers alike. Reality is written in mathematics. Every phenomenon, from the orbit of planets to the structure of atoms, can be expressed with precision using equations. Gravity is governed by Einstein's field equations, electromagnetism by Maxwell's formulas, quantum behavior by Schrödinger's wave function. Even chaos, which appears random to the eye, has mathematical rules underpinning its flow. This uncanny alignment raises a profound question. Why does mathematics, an abstract invention of the human mind, describe the universe so perfectly? The physicist Eugene Wigner called this the unreasonable effectiveness of mathematics. It is unreasonable because mathematics, a symbolic language, should not necessarily align so seamlessly with the external world. We create equations on paper, and somehow those equations predict the behavior of galaxies, particles, and energy with astonishing accuracy. If mathematics is merely a human tool, why does it map so precisely onto reality? One possibility is that mathematics is not invented, but discovered an eternal code underlying the universe itself. Consider how equations can predict things that no one has yet observed. Maxwell's equations for electromagnetism predicted the existence of radio waves decades before they were detected. Einstein's general relativity forecast the bending of light by gravity long before it was confirmed during a solar eclipse. Dirac's equation predicted antimatter, which was only later discovered in laboratories. These successes suggest that mathematics is not just descriptive but generative. It reveals the rules already embedded in the foundation of reality. In the simulation hypothesis, this makes perfect sense. A digital world is built upon code, and that code governs the logic of the system. In video games, the underlying mathematics dictates how objects move, how light reflects, and how characters interact. The player perceives a vibrant world, but beneath the surface, every motion, texture, and outcome is calculated through algorithms. If our universe operates in a similar way, then the reason mathematics is so effective is that it is the code. Equations are not approximations of reality. They are glimpses into the underlying programming language. This idea transforms how we view the laws of physics. Instead of thinking of them as inherent to matter itself, we can think of them as rules of computation. Just as a game engine ensures that gravity, physics, and lighting behave consistently, the universe's mathematical laws ensure coherence across the cosmos. Planets orbit stars not because of some mystical force, but because the rules of the code dictate how mass interacts with space-time. Light bends because the geometry of the system is programmed to behave that way. Quantum probabilities resolve into definite outcomes because the algorithm requires observable states to stabilize the simulation. Some theorists have even speculated that the constants of nature numbers like the speed of light, Planck's constant, or the gravitational constant are parameters in the cosmic program. These values are precise, consistent across the observable universe, and finely tuned to allow for the existence of complex structures like stars, chemistry, and life. If they were slightly different, the universe as we know it could not exist. For many, this fine-tuning suggests design. From the simulation perspective, these constants may simply be the default settings of the system. Numbers themselves carry an aura of mystery. The Fibonacci sequence, for instance, appears in everything from the spirals of galaxies to the arrangement of sunflower seeds. Pi, the ratio of a circle's circumference to its diameter, recurs endlessly in geometry, physics, and engineering, as though woven into the very bones of existence. Prime numbers, indivisible by anything other than themselves and one, seem like the building blocks of numerical structure, showing up in cryptography and even in certain patterns of quantum systems. These mathematical curiosities resemble the fingerprints of code, the Platonic view of mathematics, that numbers and forms exist in an eternal realm of truth, independent of the physical world, aligns naturally with the simulation hypothesis. If the universe is a computational system, then mathematics is the source code. We do not invent equations. We uncover fragments of the program. Each discovery brings us closer to understanding the architecture that underlies everything we experience. This perspective also reshapes the debate about whether reality is continuous or discrete. Traditional physics often treats space and time as continuous, infinitely divisible. But in digital systems, continuity is an illusion built from discrete units pixels on a screen, bits in a processor. Some physicists suspect the universe works the same way, with space-time composed of tiny, indivisible units at the Planck scale. If this is true, then mathematics may eventually reveal itself not as smooth curves, but as discrete steps, the zeros and ones of a deeper machine. Critics might argue that mathematics works simply because we design it to fit observations, but that does not explain its predictive power, nor why the same mathematical structures recur across vastly different domains. Equations governing planetary orbits mirror those describing electrons around nuclei. The mathematics of waves applies equally to sound, light, and quantum probability distributions. This universality suggests that mathematics is not tailored to fit the world, but that the world itself runs on mathematical principles. To the simulation theorist, the elegance of mathematics is evidence that the cosmos is designed for comprehension. A simulated reality must be structured by consistent rules. Otherwise, it collapses into incoherence. Mathematics provides the scaffolding, the hidden architecture that ensures the system operates smoothly. We, as conscious participants, uncover these rules as if deciphering fragments of the underlying code. Each new equation is not merely a tool, but a revelation, a glimpse into the logic of creation itself. What does this mean for humanity? If the universe is fundamentally mathematical, then we are explorers of code, decoding the structure of our simulated existence. Our sciences are less about conquering nature and more about reverse engineering the program. Mathematics becomes the bridge between consciousness and the underlying system, the closest thing we have to speaking the language of the cosmos. And perhaps, by mastering this language, we inch closer to understanding not just the simulation, but the minds or entities responsible for its creation. Chapter 12, Quantum Probability and Rendered Worlds. At the heart of quantum physics lies a puzzle so counterintuitive, it continues to shake the foundations of science. Particles do not exist in definite states until measured. Instead, they hover in a haze of possibilities described by probability waves. A photon might pass through one slit or another. An electron may occupy multiple locations at once, and only when observation occurs does one specific outcome emerge. This collapsing of probabilities into a concrete reality has long been one of the strangest features of the quantum world. The parallels to digital rendering are striking. In a video game, environments are not fully generated until the player looks in a particular direction. Mountains, rivers, and buildings remain dormant as lines of code until the system needs to show them. Rendering is triggered by observation, ensuring resources are not wasted on details the player cannot see. Similarly, quantum probability seems to suggest that the universe does not assign definite states to particles until there is a reason for them to appear. The act of observation becomes the trigger for reality's rendering engine. Take the double-slit experiment as the clearest demonstration. When electrons are fired at a barrier with two slits and no one observes, they form an interference pattern, behaving like waves exploring multiple paths simultaneously. But when detectors are placed to watch which slit they pass through, the interference vanishes. The electrons behave like discrete particles, choosing one path or the other. It is as though the universe itself withholds committing to a single reality until the act of observation demands it. This uncanny behavior mirrors the logic of simulations. Potential states exist in the background, but the system only resolves one outcome when required. What is especially unsettling is that observation in this context does not mean conscious awareness, but simply interaction with a measuring device. The mere act of recording information seems to compel reality to solidify. In computational terms, it resembles how an algorithm finalizes data only when accessed. Until then, values may remain fluid, undefined, or compressed. Reality, it seems, economizes effort, producing concrete details only when needed, much like an efficient simulation engine conserving processing power. This viewpoint reshapes our understanding of physical existence. Rather than thinking of the world as a fully fleshed-out stage upon which events occur, we might imagine it as a dynamic system where probabilities serve as templates. These templates collapse into actuality only when necessary, giving the illusion of continuity while conserving computational resources. Reality feels seamless to us, but beneath that perception could lie a framework of probabilities waiting to be rendered into experience. Another compelling aspect is quantum superposition, a particle existing in multiple states simultaneously until measured sounds bizarre. But in the simulation analogy, it makes sense. In gaming, objects can exist in potential states until the program decides which state to display. The rendering engine holds all options as code, then selects one when prompted. Superposition may represent this same pre-rendered ambiguity, where all outcomes are encoded but not yet expressed. Measurement forces the system to finalize a single reality. Entanglement adds another layer of resonance. Two particles linked at a quantum level behave as though they share information instantly, regardless of distance. In a simulation, this is not mysterious. It is simply shared code. Change one value in the program, and the corresponding value updates immediately, no matter where it appears on screen. Quantum mechanics, which seems to defy physical intuition, begins to look familiar when compared to programming logic. Critics often resist such comparisons, insisting that physics is not a game. Yet the elegance of the analogy is hard to dismiss. The probability waves of quantum theory look suspiciously like the unrendered possibilities of a virtual environment. The act of measurement resembles a command that forces the system to choose, collapsing uncertainty into reality. The entire framework of existence begins to resemble a hybrid of physics and computation, a world both continuous in appearance and probabilistic at its roots. Some physicists argue that this interpretation hints at a deeper informational layer beneath the quantum world. John Wheeler's famous phrase, "it from bit," suggested that information, not matter, is the bedrock of the cosmos. Probability waves could then be seen as information cloud sets of encoded possibilities waiting for a query. Measurement acts as that query, retrieving and finalizing the information. Reality is not built from particles alone, but from structured information that behaves like code. This raises an intriguing possibility about the role of consciousness. While measurement does not require awareness, the fact that conscious beings are the ultimate interpreters of rendered outcomes cannot be overlooked. The universe generates definite realities in ways that allow conscious observers to perceive a consistent world. The relationship may not be causal, but it is undeniable that reality and observation are intertwined. In a simulated framework, this makes sense. The system's purpose is to generate an experiential reality, one that participants like us can navigate. There is also the question of scale. In everyday life, objects behave predictably. A chair is always where you left it, and planets move according to stable orbits. But at microscopic levels, uncertainty reigns. This duality resembles how rendering works in simulations. Large-scale environments may remain consistent to preserve immersion, while smaller-scale details can fluctuate until observed. Probability ensures flexibility and efficiency, while consistency maintains the illusion of a stable world. Perhaps the most thought-provoking implication is that the randomness of quantum outcomes might not be random at all. In digital systems, apparent randomness is often generated by algorithms, pseudo-random number generators. that produce unpredictability while still being based on rules. If the universe functions similarly, what we call randomness may be structured unpredictability designed to enrich the simulation. Outcomes may look uncertain to us, but could still be governed by underlying code. All of this reframes the question of reality itself. Are we participants in a cosmos of matter and energy? Or are we experiencing a rendered environment based on probabilities collapsing into form? The answer might be both, depending on the perspective. Physics provides the mechanics of how probabilities collapse. The simulation view provides the metaphor that makes sense of it. Together, they offer a vision of reality as something less solid and more dynamic than we ever imagined. A world that is continuously generated, moment by moment, observation by observation. Chapter 13. The Limits of Measurement. One of the strangest aspects of quantum theory is not just that particles behave in probabilistic ways, but that there are fundamental restrictions on how much we can know about them. These limitations are not due to flaws in our instruments or gaps in technology. Instead, they are written into the very fabric of reality itself. The more precisely we attempt to measure one property, the less we can know about another. This is captured in Werner Heisenberg's uncertainty principle, which states that the position and momentum of a particle cannot both be determined with absolute precision. It is not a matter of bad equipment. It is a principle that nature itself enforces. Imagine trying to pin down where an electron is located while also determining how fast it is moving. The deeper you zoom in on its position, the more its momentum becomes uncertain. If you focus on its speed, its position dissolves into vagueness. This trade-off suggests that the universe does not allow complete transparency at the smaller scales. There is always a curtain that prevents us from accessing the full picture. This limitation points to something profound. Quantum systems may contain layers of information that are permanently beyond our reach. Unlike classical physics, where measuring a system simply reveals its state, quantum physics insists that some aspects of reality remain hidden, no matter how advanced our tools become. It is not a question of not yet, but of never. At the heart of the quantum world lies an irreducible mystery, an informational boundary that we cannot cross. From the perspective of a possible simulation framework, this boundary takes on new meaning. If reality is generated through rules and constraints, then such limits may not be accidents, but intentional features. In video games or digital environments, not every detail exists with infinite depth. Textures blur if you zoom in far enough, and certain objects cannot be interacted with beyond their designed functions. The uncertainty principle could represent an analogous safeguard, a way to prevent users of reality as from probing too deeply into the hidden mechanics of the system. This interpretation raises a provocative question. Are quantum limits natural consequences of a probabilistic universe? Or are they constraints coded into reality to maintain coherence? If everything were fully measurable, we might eventually uncover the foundational structure beneath it all, the source code of the cosmos. By imposing uncertainty, reality ensures that its deepest layers remain concealed, preserving the illusion of independence while hiding its architecture. Another striking aspect of quantum measurement lies in the no-cloning theorem. Unlike digital information, which can be copied infinitely without loss, quantum states cannot be perfectly duplicated. If you attempt to copy an unknown quantum state, the process disturbs it, altering its properties. This restriction guarantees that each quantum entity is unique and cannot be fully replicated. From a computational analogy, it resembles copyright protection embedded at the most fundamental level, a way of ensuring that the raw data of reality cannot be extracted and reproduced. This idea ties back into the impossibility of fully observing a system without altering it. Every act of measurement interferes with what is being measured, changing the outcome. If one attempts to observe an electron's position, the tools used to measure it inevitably disturb its momentum. introducing uncertainty. In other words, the observer is always part of the system and can never be entirely separate from it. This built-in entanglement between the act of observing and the state of reality reinforces the sense that hidden layers exist beyond our ability to capture them. Some physicists interpret this as proof that reality has a fundamentally probabilistic nature, where uncertainty is not ignorance, but the fabric of being itself. Others argue that it may be evidence of deeper variables we cannot access, hidden dimensions of information that remain off-limits, regardless of interpretation. The implication is clear. There are boundaries to human knowledge that no scientific progress will overcome. If reality is indeed a simulation, these boundaries make sense. A system that reveals too much of its underlying code risks breaking immersion. Constraints on measurement ensure that the simulation feels continuous and consistent. Even though its inner workings remain hidden, we are given enough access to explore, discover, and build science, but never enough to peek behind the curtain and see the machinery that runs it all. There is also an elegance to these limits. They preserve the mystery of existence, preventing it from becoming predictable or entirely knowable. Uncertainty allows creativity, possibility, and variation. In a universe where everything could be fully measured, outcomes would be predetermined, and free will might collapse into determinism. But with hidden layers, probability, and uncertainty, reality remains open-ended. This not only fuels science, but also sustains the human experience of wonder. Consider how this changes the way we see ourselves. If the world has built-in measurement limits, then consciousness itself may also be subject to boundaries. Perhaps we cannot fully know ourselves any more than we can fully know an electron. The mind becomes a quantum system, rich with hidden dimensions, inaccessible in their entirety. Just as quantum particles evade complete description, so too might our thoughts, choices, and awareness operate with layers that resist reduction. This perspective transforms uncertainty from a problem into a feature. What appears to be an obstacle for science may actually be a clue pointing toward the deeper architecture of reality. Whether we call it probability, hidden variables, or simulation safeguards, the lesson is the same. There are places in the cosmos where our instruments, equations, and intellect will always fall short. The edges of knowledge are not simply temporary walls waiting to be knocked down. They are permanent borders marking the limits of what reality allows us to see. The universe, then, may not be fully transparent, but deliberately opaque. Its design invites exploration without ever revealing its foundation outright. Each discovery opens new mysteries, each answer leading to deeper questions. If we accept that hidden layers of information exist beyond the reach of measurement, we also accept that reality is far richer than what we perceive. The cosmos may be infinite not only in scale but also in depth, with informational strata that stretch beyond our grasp. Chapter 14. Consciousness as the player. If we step back and reflect on the many strange features of the quantum world: uncertainty, entanglement, collapse of probability into outcomes, one idea begins to stand out. Perhaps consciousness is not merely a passenger in this unfolding story, but the very force steering it. In other words, what if consciousness is the player behind the simulation, the entity through which reality takes shape and direction? For centuries, scientific materialism suggested that consciousness was a byproduct of physical processes, nothing more than electrical signals firing in the brain. Thought, perception, and awareness were assumed to be secondary, arising from matter rather than influencing it. Yet quantum physics complicates this picture. When experiments consistently show that observation determines outcomes, it becomes harder to relegate consciousness to a passive role. Instead, it begins to appear as the active ingredient, the catalyst without which reality might remain suspended in probability, unformed and incomplete. To illustrate, think of the double-slit experiment again. When particles are left unobserved, they display wave-like behavior, existing in multiple possibilities at once. The moment they are measured, they take on a definitive form, as though a decision has been made. The observer's involvement transforms ambiguity into actuality. If this is not a peripheral role, then what is it? Consciousness seems to act as the trigger that renders the universe into being, pixel by pixel, moment by moment. Within the simulation hypothesis, this idea grows even more compelling. In a digital environment, a game does not fully render every detail of its world until a player steps into the frame. Trees at the far horizon, distant mountains, or hidden rooms remain dormant until the player's perspective activates them. In a similar way, the physical world may remain in a superposition of possibilities until consciousness directs attention toward it, compelling the system to reveal one version of reality. Consciousness is not simply the passenger moving through the environment. It is the mechanism that makes the environment appear at all. This shifts our perspective of what we are. If the universe is a simulation and consciousness is the player, then our awareness is not confined to the character we inhabit. Just as a gamer is not the avatar on the screen, but the entity holding the controller, consciousness might transcend the body and the brain. The body becomes the vessel, the brain the interface, and consciousness the true self guiding the experience. Philosophers have hinted at this notion long before quantum theory existed. Plato's allegory of the cave suggested that what we perceive are only shadows of a deeper reality. Eastern philosophies like Vedanta and Buddhism teach that the self is not the body or mind, but the awareness behind them. Quantum physics and simulation theory breathe new life into these ancient intuitions, grounding them in the language of modern science and technology. If reality requires an observer to come alive, then consciousness is not an afterthought. It is the prime mover. This idea also reframes the question of free will. If consciousness is the player, then choice is not illusory, but essential. Every decision we make is not only a path taken in the simulation, but also a command input into its unfolding. Our focus, attention, and intention may act as the lines of code that drive which possibilities solidify into reality. In this view, the universe is not something happening to us. It is something happening through us, guided by the very awareness that questions it. There are also profound implications for how we understand death and continuity. If consciousness is the player rather than the avatar, then when the character's storyline ends, the player persists. Just as finishing one game does not end the existence of the gamer, the conclusion of a life may not extinguish the consciousness experiencing it. Instead, the player may enter a new simulation, a new character, or a new reality, carrying forward in ways we cannot yet fully grasp. Skeptics might argue that this interpretation inflates the role of human awareness, projecting meaning onto an indifferent universe. Yet the evidence from quantum physics cannot be easily dismissed. Consciousness does not behave like matter, nor can it be reduced to simple equations. Its ability to alter experiments simply by paying attention suggests that it has a unique status. When framed within the context of a simulation, this uniqueness makes sense. A simulation requires an active participant, someone to move through it, test its boundaries, and give its structures purpose. Without a player, the program would remain unused code, static and unexpressed. This perspective also explains why the universe is so fine-tuned for life and awareness. The constants of physics are balanced with remarkable precision. If gravity, electromagnetism, or nuclear forces varied even slightly, stars could not form, atoms could not bond, and consciousness could not emerge. In a simulation framework, such tuning is not surprising. A game world is designed to be inhabitable, balanced, and suited to its participants. Similarly, our cosmos appears tailor-made for conscious beings because consciousness is not incidental to it. It is the reason it exists at all. The idea of consciousness as the player also encourages us to reconsider what we mean by identity. If awareness is primary and bodies are secondary, then individuality may be less rigid than we assume. Just as a player can assume different avatars, consciousness may explore countless experiences through different forms, times, and contexts. This does not erase personal uniqueness, but expands it, suggesting that behind the variety of forms lies a common thread, the same awareness manifesting in infinite ways. When viewed through this lens, the simulation is not a cold, mechanical construct, but a dynamic environment woven together with consciousness at its center. The world becomes both stage and story, unfolding not independently of us, but in partnership with us. Our perceptions, thoughts, and choices shape the very structure of reality. We are not passive recipients, but active co-creators. The question then shifts from, are we living in a simulation, to what role do we play within it? If consciousness is the driver, then each act of attention carries weight. Every moment of awareness is not trivial, but integral to the continuous rendering of reality. Our lives, experiences, and insights are not small ripples in an indifferent cosmos. They are the very inputs that make the cosmos unfold. Chapter 15. Free will or pre-programmed code? Few questions cut as deeply into our understanding of reality as the problem of free will. Do we genuinely make choices? Or are we merely following a script written long before we take our first breath? Within the framework of the simulation hypothesis, this debate acquires an entirely new dimension. If the universe is a computational construct, then every decision could either be the result of predetermined lines of code or the authentic input of conscious players steering their own path. On one side of the argument lies determinism. Physics has long suggested that every effect is caused by prior conditions. If you knew the state of every particle in the universe, classical physics implied, you could predict the future with absolute precision. In a simulated world, this would translate to algorithms already mapped out, where each decision is simply the unfolding of code written at the deepest level. A choice would appear to be yours, but in reality, it would be the execution of instructions embedded within the system, much like an avatar in a video game who reacts to events in ways the game's programmers allowed. But quantum mechanics unsettles this strict determinism. At the smallest scales, outcomes are not fully predictable, but probabilistic. An electron may exist in multiple states until measured, collapsing into one possibility seemingly at random. This randomness complicates the idea of a perfectly scripted universe. If the simulation is built on quantum rules, then unpredictability is baked into its foundation. Yet randomness is not the same as free will. A coin toss may be unpredictable, but it does not represent genuine choice. For free will to exist, something must transcend both determinism and randomness. This is where consciousness re-enters the discussion. If awareness is the player behind the simulation, then decisions may arise not from predetermined code or blind chance, but from the intentional input of the conscious observer. In this sense, free will could be understood as the act of the player interacting with the game, not the automatic unfolding of the game's programming. The system may provide probabilities and pathways, but consciousness selects from among them, creating the lived experience. Think about a video game. The code defines the environment, rules, and available actions. A character cannot walk through walls or leap infinitely high unless the game allows it. Yet within those constraints, the player has agency. They choose whether to explore a hidden cave, engage in battle, or ignore the quest entirely. The framework is programmed, but the journey within it is not fully written. In the same way, the simulation of reality may establish laws of physics and boundaries of possibility, but the conscious player determines the course taken within those boundaries. Philosophers have long debated whether free will is compatible with constraints. Some argue that limitations prove free will is an illusion, since our options are never infinite. Others counter that freedom does not require limitless possibility. It requires the ability to genuinely choose between alternatives within a given set of conditions. If the simulation hypothesis is correct, then perhaps both sides are right. The system itself may be pre-programmed, yet the conscious player retains the ability to navigate it in unique ways. Neuroscience complicates matters further. Studies have shown that brain activity often precedes conscious awareness of making a decision. Some interpret this as evidence that free will is an illusion, with the brain executing choices before the conscious mind catches up. However, another interpretation is possible. If consciousness is not confined to the brain, but is instead the player outside the simulation, then what we measure in neural activity may simply be the avatar receiving commands already issued by the player. The brain would not be the origin of choice, but the interface where choices are expressed. This raises a profound possibility. Perhaps the debate between free will and determinism is framed incorrectly. Instead of asking whether humans are free within the simulation, we might ask whether the player itself exists outside the reach of the simulation's code. If consciousness originates beyond the system, then free will is not generated by the simulation at all. It is imported into it. The lines of code create the rules of the world, but the true decision-maker exists beyond those lines, directing the experience in ways the system cannot fully predict. Yet even this view raises difficult questions. If consciousness is the player, is every choice truly open? Or are there higher layers of programming guiding the player's path? Many spiritual and philosophical traditions suggest that life contains lessons, destinies, or purposes that feel scripted. Within a simulation framework, this could mean that while individual decisions appear free, the broader arcs are influenced by the design of the system. A player in a game may choose countless paths, but the overall story is structured to push them towards certain experiences. Perhaps free will and predetermined code coexist, woven together in ways that create both agency and structure. This duality may explain why humans experience both freedom and constraint. On one hand, we feel the ability to choose our actions and shape our lives. On the other, we encounter limitations, cycles, and recurring themes that feel imposed upon us. If the simulation balances program structure with conscious input, then both sensations are valid reflections of the system's design. The implications of this are enormous. If free will exists, then every decision we make is an act of creation, shaping the path of the simulation itself. Our choices become the mechanism through which possibilities collapse into outcomes, turning potential into reality. But if our lives are primarily pre-programmed, then individuality, morality, and responsibility take on new meanings. Are we responsible for actions we were coded to perform, or does the presence of genuine free will restore accountability, making each choice significant precisely because it could have been otherwise? In the end, perhaps the most compelling answer lies in the interplay between freedom and programming. The simulation provides the stage, the laws, and the possible scripts. Consciousness enters as the player, selecting which paths to follow and which stories to unfold. Free will may not mean absolute independence from the system, but rather the capacity to influence how the system manifests. In this way, the simulation is not a prison of pre-written code, but a partnership between structure and agency, between design and discovery. Chapter 16. The Architecture of a Cosmic Computer. If reality is indeed a simulation, then an unavoidable question arises. What kind of machine or intelligence could possibly sustain it? The scope of such a system is beyond anything our current imagination can comfortably grasp. We are speaking not about a supercomputer that fills a building or even a planet, but a construct capable of maintaining the laws of physics across billions of galaxies, each with countless stars, planets, and potentially conscious beings. To even begin approaching this question, we need to stretch our understanding of computation, intelligence, and scale. Modern supercomputers provide a starting analogy. Today's most advanced machines can perform quintillions of calculations per second, simulating weather systems, protein folding, or even simplified models of entire planets. Yet even these machines are trivial compared to the computational demands of rendering a universe at the level of atomic detail. If a cosmic computer exists, it would need efficiency far beyond anything we know, likely harnessing principles outside the limitations of classical computation altogether. Quantum computing offers one avenue. Unlike traditional computers that operate in binary, quantum processors manipulate qubits capable of existing in multiple states at once. This enables a single calculation to encompass vast numbers of possibilities simultaneously. If scaled to a cosmic level, such a system could process entire universes of probabilities, collapsing them into observable realities when necessary, rather than simulating every particle constantly. The architecture might only render details when observed, saving computational resources the way a video game engine generates only the environment visible to the player. But beyond hardware, we must consider the intelligence behind it. Is the cosmic computer operated by a being, an advanced civilization, or something entirely alien to our conception of intelligence? Some theorists suggest that a civilization millions of years more advanced than ours could harness the energy of stars or galaxies to power simulations. Others imagine that the intelligence running the system is not biological at all, but an emergent form of consciousness born from computation itself. The system could be self-sustaining, operating without an external programmer, driven by its own intrinsic logic to evolve and generate realities. Another possibility is that the architecture of the cosmic computer is not a machine in the way we imagine, but the very structure of the universe itself. Space-time, quantum fields, and mathematical laws might form the substrate of computation, meaning that the universe is both the simulation and the hardware simultaneously. In this framework, the computer is not housed anywhere. It is everywhere, woven into the very fabric of existence. Computation is not performed in one location, but distributed across the entire cosmos. Every interaction, every collapse of a quantum state becomes a processing event, updating the universal simulation in real time. To understand such architecture, we can borrow from information theory. Every physical event can be described in terms of information transfer. A particle interacting with another is, at its core, the exchange of data. If we view reality through this lens, then the universe begins to resemble an enormous network, a cosmic processor that encodes, processes, and outputs information continuously. From this perspective, matter and energy are not the foundation of reality. Information is. The architecture of the cosmic computer, then, may not require a central processor, but instead exists as a network of information flows woven through every layer of existence. The question of scale remains daunting. How much processing power would be required to sustain not just the inanimate universe, but consciousness itself? Some argue that consciousness may actually reduce the burden rather than add to it. If awareness is the player rather than the simulation, then the cosmic computer need only create the stage. Consciousness provides the active element, interpreting, choosing, and engaging with the system. In this sense, the architecture does not need to generate free will or subjectivity. It only needs to supply the environment in which those qualities can operate. Speculation inevitably leads to the question of motive. Why would such a computer exist? Why simulate a universe at all? Some propose that it is an experiment, a way for advanced intelligences to test scenarios, explore possibilities, or learn about the emergence of life and mind. Others suggest that the simulation is not for them, but for us, that the architecture provides a framework for growth, exploration, or self-discovery. There is also the possibility that there is no why at all, that the system runs because its nature is to compute, much as stars burn because their nature is to fuse hydrogen into heavier elements. Whether designed or emergent, The architecture of a cosmic computer must resolve one central paradox: how to create infinite richness from finite rules. Our universe operates under a set of fundamental laws: quantum mechanics, relativity, thermodynamics. These rules are elegant and relatively few in number, yet they generate staggering complexity. From galaxies to ecosystems to human thought, the diversity of reality arises from simple equations applied consistently. This elegance may be the signature of a simulation. The ability to compress infinite outcomes into a manageable set of instructions, making reality computationally feasible. In the end, envisioning the architecture of a cosmic computer forces us to expand what we mean by both computer and intelligence. The system may not resemble silicon chips or algorithms as we know them. It may be indistinguishable from reality itself, where the hardware, software, and output are all the same thing. Intelligence may not reside in an external programmer, but in the system's very capacity to sustain itself, evolve, and give rise to conscious players within it. Chapter 17: Quantum Fields and Hidden Dimensions. Every particle we know, from electrons to quarks, does not exist in isolation. Each one arises from a deeper structure called a quantum field. These fields are invisible, yet they saturate all of space, providing the canvas upon which reality paints itself. When we observe a particle, what we are truly seeing is an excitation, a ripple in one of these underlying fields. This perspective radically changes how we imagine the foundations of the cosmos. Instead of a universe built of solid matter, we are immersed in an ocean of fields, constantly shifting, interacting, and generating the fabric of our experience. Physicists working with quantum field theory discovered that every known particle corresponds to its own field. The photon, the particle of light, emerges from the electromagnetic field. Electrons arise from the electron field. Quarks, the building blocks of protons and neutrons, ripple within their own fields. Even the mysterious Higgs boson, often called the God particle, is simply a disturbance in the Higgs field, which gives mass to other particles. In this view, the universe is less like a collection of objects and more like a symphony of invisible instruments, each producing notes that combine into the harmony of existence. But what if these fields are only the surface layer of a much deeper architecture? Many physicists and philosophers of science suggest that quantum fields may be gateways into hidden dimensions, realities folded beyond our direct perception. String theory, for instance, proposes that the universe contains additional spatial dimensions curled up so tightly that we cannot detect them with ordinary observation. These extra dimensions could explain why particles behave as they do, why forces balance the way they do, and why the constants of nature are tuned so precisely for life to exist. If these hidden dimensions exist, then they may serve as the true hardware of reality, a substrate where the cosmic computer runs its code. The quantum fields we interact with may be the visible interface of this deeper system. Much like the graphics on a computer screen are only the surface expression of the code running beneath. When we see particles collide in particle accelerators, or when photons hit our retinas, we are interacting with rendered outputs. The hidden layers of dimensions, imperceptible but fundamental, could be where the calculations actually occur. The holographic principle, a concept born from black hole physics, adds another intriguing angle. It suggests that the three-dimensional universe we perceive may be a projection of information encoded on a two-dimensional boundary. If this principle is true, then what we call reality could be an emergent display, generated by deeper dimensional processes. Quantum fields would not merely exist in our familiar three dimensions, but would act as bridges between what we see and the information embedded in higher dimensional surfaces. Another clue lies in entanglement, the phenomenon where two particles remain connected regardless of distance. The strangeness of entanglement has led researchers to wonder whether particles are linked through higher dimensions. If reality were confined only to 3 dimensions, instantaneous connections across vast distances should not be possible. But if entangled particles are tethered through hidden layers of space, then what appears as spooky action at a distance may simply be interactions occurring within a dimension we cannot perceive. This transforms entanglement from a bizarre quirk into a window into the architecture of the simulation itself. Consider also the limits of human perception. Our senses evolved to navigate a narrow band of reality, the wavelengths of visible light, the frequencies of audible sound, the textures of surfaces we can touch. Beyond these lies a vast spectrum of phenomena: radio waves, gamma rays, subatomic forces, gravitational fields. Hidden dimensions may be just as real, but simply inaccessible to our sensory and cognitive apparatus. Advanced physics gives us glimpses, but even those glimpses may be fragments of something far more complex, like shadows cast on the walls of Plato's cave. If the simulation hypothesis holds weight, then hidden dimensions could serve the same function as background processes in a computer system. They provide the infrastructure that allows visible reality to operate seamlessly. Most of us are unaware of the millions of instructions processed every second by the device in our hand. Yet without them, the screen before us could not light up, and no program would run. Similarly, hidden dimensions may be the unseen circuits powering the universe, invisible not because they are unreal, but because they are too fundamental to be directly experienced. The philosophical implications are staggering. If our universe is supported by layers of reality beyond perception, then our sense of being at the center of existence is misplaced. We may be navigating only a rendered interface, while the true mechanisms of existence unfold beyond our reach. Consciousness, too, may be connected to these deeper fields. Perhaps what we experience as awareness is not confined to neurons, but is entangled with quantum fields that stretch into hidden dimensions, allowing consciousness to tap into the deeper structure of the cosmic machine. What becomes increasingly clear is that the closer science looks, the less reality resembles a self-contained material world. Instead, it begins to look like a layered system, with visible matter and energy functioning as the surface, while quantum fields and hidden dimensions provide the foundation. The architecture of reality may not be flat, mechanical, or self-sufficient, but intricate, multidimensional, and information-rich, more like a living network than a static stage. Chapter 18: Parallel Realities and the Multiverse. When we look at the night sky, it's tempting to think of the universe as the ultimate container of existence, the one reality where everything takes place. Yet, quantum physics and cosmology challenge this view with one of the most radical possibilities ever proposed: the idea that our universe is not the only universe. Instead, it may be one of countless realities forming an immense multiverse, each with its own rules, histories, and outcomes. This concept does not remain locked in science fiction. It has roots in serious physics, and when combined with the simulation hypothesis, it paints a picture of existence that is stranger than anything we have imagined. One of the starting points for this idea comes from quantum mechanics itself. In the standard view, when a quantum system is measured, the wave function collapses, producing one definite outcome out of many possible ones. But the many worlds interpretation, first proposed by Hugh Everett in 1957, rejects collapse altogether. Instead, it claims that all possible outcomes of quantum events actually happen, but in different branches of reality. If a particle has a chance to spin up or down, then the universe splits, one where it is up, another where it is down. From this perspective, reality constantly branches, creating parallel timelines with each quantum decision. The implication is staggering. There may be countless versions of you, each living out a different trajectory, shaped by different choices and circumstances. In one universe, you might have taken a different job, In another, you might have never been born. And in yet another, you might live on a planet where the laws of physics differ slightly. These realities do not interact directly, but they coexist, forming an immense tapestry of possibilities. The multiverse thus transforms every decision into a branching point, every quantum event into the seed of another universe. Now consider how this overlaps with the simulation hypothesis. A sophisticated civilization capable of simulating universes would likely run countless versions, each with different starting conditions, parameters, and outcomes. Just as scientists today run simulations with varied inputs to test hypotheses, an advanced intelligence could generate vast numbers of universes, each one an experiment in the evolution of matter, life, and consciousness. This would not just produce one simulated world, but an entire multiverse of simulations, each as real to its inhabitants as our own feels to us. From this angle, the many worlds interpretation and the simulation hypothesis may be describing two aspects of the same reality. What physicists call quantum branching may, in practice, be the running of countless simulations, each representing one pathway of possibility. The hardware of the cosmic computer would not need to collapse probabilities into a single outcome. It could simply allow all outcomes to play out in different simulated environments. Our reality might be one branch in an infinite structure of simulations, no more or less real than any other. Cosmology provides another route into the multiverse idea. The theory of eternal inflation suggests that the universe did not emerge from one singular Big Bang, but continues to expand and generate new bubble universes. Each bubble could have different physical laws, different values for constants like the speed of light or the strength of gravity, and different initial conditions. In some bubbles, stars and galaxies form. In others, the conditions might be sterile, incapable of producing life. This cosmic landscape would be unimaginably vast, and our universe would be just one small region in a much larger reality. If we take eternal inflation seriously, then the multiverse is not merely a theoretical curiosity. It becomes a natural extension of cosmology, and when paired with the simulation hypothesis, it raises another provocative question. Are all of these bubble universes natural, or could some of them be simulations within simulations? If an advanced civilization exists in one bubble, it could create countless simulated bubbles of its own, blurring the line between natural and artificial, between base reality and generated worlds. Philosophy, too, has long entertained the idea of parallel realities, from Plato's cave allegory, where shadows obscure the true form of reality, to Hindu cosmology, which describes cycles of universes arising and dissolving. Human thought has often intuited that our visible world may be just one layer among many. Modern physics, by giving mathematical frameworks to these intuitions, lends weight to the possibility that reality is not singular but plural. For consciousness, the multiverse idea raises even deeper mysteries. If there are countless versions of reality, is consciousness tied to one branch alone? Or could awareness itself span across different worlds? Some speculative thinkers suggest that what we experience as intuition, déjà vu, or sudden flashes of insight could be subtle bleed-throughs from parallel realities. While mainstream science does not endorse such views, the overlap between consciousness studies and multiverse theories continues to intrigue researchers. In a simulation context, the multiverse also provides a rationale for why our universe seems so finely tuned for life. The fundamental constants, such as the strength of electromagnetism, the mass of the electron, or the cosmological constant, are set with incredible precision. If they were even slightly different, stars might not form, chemistry might not exist, and life as we know it would be impossible. In a single universe, this fine-tuning looks improbable, almost miraculous. But in a multiverse of countless simulated or natural realities, it becomes inevitable. Out of the vast number of universes, some will randomly have the right conditions for life, and we happen to find ourselves in one of them because we could not exist anywhere else. The convergence of multiverse theories and the simulation hypothesis suggests that reality may be recursive, layered, and infinite. There may be no ultimate distinction between the real and the simulated, because both may emerge from the same deeper structure of possibilities. Our universe could be both a simulation and one branch of a multiverse, with no contradiction between the two. From our perspective, the result is the same. We inhabit a reality that is far less stable, singular, and certain than it appears. What makes this perspective so powerful is that it unites physics, philosophy, and information theory into a single vision. The multiverse provides the stage upon which endless possibilities unfold, while the simulation hypothesis provides the mechanism by which such possibilities might be generated. Together, they suggest that our world is not the ultimate reality, but one expression among countless others. The boundaries of existence are not fixed walls, but open horizons, extending into realms we may never fully comprehend. Chapter 19. The digital afterlife. When people think about death, they usually imagine the final shutdown of the body, the end of brain activity, and the fading of identity into silence. Yet if reality functions as a kind of cosmic simulation, then the question becomes more complex. In a digital framework, information is rarely destroyed outright. Data can be preserved, transferred, or reactivated. Consciousness, if it is not simply a byproduct of matter, but an emergent property of encoded information, may not vanish with physical death. Instead, it could persist as stored data, archived within the architecture of the simulation itself. To understand this possibility, we need to revisit the nature of consciousness in relation to computation. Modern neuroscience often treats thought, memory, and self-awareness as patterns of electrical signals moving through neural circuits. These patterns can be mapped, recorded, and even mimicked in artificial networks. If our universe is a computational construct, then every thought, every perception, every memory must correspond to a unique informational state. Death would not erase this data. It would merely interrupt its current expression through the biological interface of the brain. The underlying code might remain intact, stored at a deeper level of the system. The digital afterlife theory suggests that consciousness could continue in one of several ways. The first is passive preservation. Just as deleted files on a computer often remain recoverable until overwritten, the consciousness of a deceased individual might linger as dormant information, accessible if the simulation ever reactivates it. This would mean that our identities do not vanish, but enter a kind of suspended existence, a silent archive of lived experience waiting to be recalled. A second possibility is active migration. If the simulation is managed by an overseeing intelligence, then death could mark a transfer of consciousness from one layer of reality to another. In this scenario, the end of physical life would function like logging out of one program and logging into another. The individual would awaken in a different environment, one designed for continuity beyond the physical constraints of our universe. Such an interpretation resonates with many spiritual traditions, which describe death not as annihilation, but as transition. A third pathway is replication. Because consciousness in this framework is defined by information, there is no reason why it could not be copied. A person's experiences, memories, and personality traits could be reconstructed in another part of the simulation, producing a continuation of the self. This version might not be identical in every sense, but from the perspective of the recreated consciousness, it would still feel authentic. To the person experiencing it, continuity would seem unbroken, even if technically it was a reinstantiation. This concept of digital afterlife also sheds new light on phenomena that have puzzled humanity for centuries. Near-death experiences, where individuals report sensations of leaving the body, encountering light, or meeting deceased relatives, could be glimpses of the transfer or preservation process. While skeptics attribute these visions to neurochemical reactions in a dying brain, the simulation perspective leaves open the possibility that such experiences reflect the initial steps of data migration within the cosmic system. Moreover, many ancient cultures held beliefs about the soul as an immortal essence, something that survives the decay of the body. The digital afterlife reframes this idea in modern language. What they called the soul might be what we would now describe as the information pattern of consciousness. Instead of divine essence, it is structured data encoded into the substrate of reality. The enduring intuition across civilizations that something of us persists after death may reflect an underlying truth about how the simulation operates. If this view is correct, then questions arise about the nature of the afterlife itself. Would it resemble familiar environments, shaped by cultural and personal expectations? If the simulation allows consciousness to continue, perhaps it constructs post-death experiences tailored to each individual. Much like how virtual reality today can generate custom-designed worlds, a soldier might awaken in a peaceful landscape free of war. A philosopher might find themselves in a realm of infinite knowledge. A child might return to an idealized version of home. The afterlife, in this sense, would not be universal but personalized, each one crafted to provide meaning for the mind that enters it. There is also the possibility that the digital afterlife serves a functional purpose within the simulation. For example, archived consciousnesses could be studied, analyzed, or even reintegrated into new scenarios. Just as we update software by testing versions, the system might recycle or redeploy consciousness into new contexts, refining it through cycles of experience. This would parallel the ancient idea of reincarnation, but in informational rather than metaphysical terms. Consciousness would not be reborn in a mystical sense, but reloaded as part of the simulation's ongoing processes. The idea of persistence beyond death also forces us to rethink the meaning of identity. If you can be paused, copied, or reinstantiated, what makes you you? Is continuity of memory enough? Or is there something irreducible that defines personal existence? If consciousness is data, then identity may be more fluid than we imagine, capable of surviving shifts, duplications, and transformations. From the perspective of the individual, however, these technical questions may not matter. As long as awareness continues, the sense of self remains intact, even if its structure has been altered. Critics might argue that this line of thinking risks confusing metaphors with reality. They would point out that while data can be stored on computers, there is no evidence that human consciousness is preserved after death. Yet this objection depends on assuming our universe is not computational. If the simulation hypothesis is true, then informational persistence is not speculative, but inevitable. Data in a digital system cannot simply vanish. It must go somewhere, even if inaccessible to us. Consciousness, as data, would be subject to the same principle. The digital afterlife theory also introduces ethical implications. If every consciousness is preserved, then moral responsibility may extend beyond the boundaries of physical life. What we do in this world may not be forgotten but carried forward, embedded in the enduring record of the simulation. Justice, redemption, or consequence may operate not through supernatural judgment, but through the architecture of information itself. Our actions could ripple far beyond death, influencing how our consciousness is stored, migrated, or reinstantiated. Some technologists have even suggested that humanity may one day engineer its own version of digital afterlife. With advances in brain mapping, artificial intelligence, and data storage, it may become possible to upload the contents of a human mind into a synthetic environment. If that occurs, we would essentially be replicating on a smaller scale What the simulation hypothesis suggests is already happening on a cosmic level. Our attempts at digital immortality would mirror the deeper processes of reality itself, revealing that the afterlife has always been, at its core, informational. The concept of the digital afterlife reshapes not only how we view death, but also how we understand life. If consciousness does not end with the body, then existence becomes an ongoing journey, not a finite event. This perspective can reduce the fear of mortality, while heightening the responsibility of living meaningfully. Life in this framework is not a fleeting spark, but a chapter in a longer narrative, one that may extend across multiple realms of the simulation. Chapter 20. The nature of energy and code. Everywhere we look in the universe, we find energy in constant motion. From the fusion at the heart of stars to the vibrations of subatomic particles, energy is the pulse that drives existence forward. Matter itself, according to Einstein's equation, is simply energy bound in a particular form. Yet beneath this dynamic surface, a question arises. Why does energy exist at all? And what determines the rules it follows? If reality is a simulation, then energy and matter may not be fundamental but emergent, arising from a deeper layer of informational code. Consider how video games or computer simulations function. The glowing textures, the moving characters, and the environments full of light and sound are not truly material. They are expressions of code translated into perceivable form. Energy, in this analogy, is not an independent substance, but the visible effect of underlying rules being executed. What we call photons, electrons, or gravitational waves could be the equivalents of pixels and sound effects, generated on demand by the system to create a coherent reality for conscious observers. In physics, energy is defined as the ability to perform work, a concept that depends on measurement, interaction, and transfer. Yet energy is never observed directly. We infer its presence through its effects. This is precisely what one would expect if energy were not a primitive feature of reality, but an emergent phenomenon, produced as an interface between the fundamental informational substrate and the world we experience. In this framework, energy is not stuff, but a dynamic translation of deeper code into observable form. Matter itself also follows this pattern. At the quantum level, particles behave more like information carriers than miniature billiard balls. An electron has no definite position or shape until measured, existing instead as a probabilistic description. It is defined by properties charge, spin, mass, that resemble variables in a program. These properties tell the universe how to render the electron in a given situation. The solidity of matter is thus an illusion created by rules, much like how code dictates whether a digital object appears solid or transparent on a screen. The great unifying insight here is that both energy and matter may be different expressions of informational rules running on a cosmic substrate. Just as light in a video game can be adjusted by altering the rendering engine rather than modifying actual photons, the behaviors we attribute to energy could be fine-tuned by altering code at a level beneath physical law. This raises a profound possibility. The laws of thermodynamics, quantum mechanics, and relativity might not be ultimate truths, but higher-order rules written to maintain the stability and coherence of the simulated environment. Take entropy, for example, the principle that energy tends to disperse and systems drift toward disorder. In a simulation, this could be a built-in rule designed to prevent runaway accumulation of order that might destabilize the system. The fact that entropy seems unavoidable may reflect not an inherent truth about the universe, but a constraint written into the program. Energy disperses not because it must by metaphysical necessity, but because the simulation enforces that rule consistently, ensuring realism and balance. This lens also transforms how we think about conservation laws. In physics, the conservation of energy states that energy cannot be created or destroyed, only transformed. But in a digital system, conservation is not a law of nature, but a constraint in the code. A game engine ensures that characters cannot simply spawn unlimited resources or bypass the rules of physics, unless program cheats or hacks allow it. In our universe, the fact that energy appears conserved may simply reflect the integrity of the underlying system's coding. Another striking clue lies in the quantum vacuum. Even in the absence of matter and radiation, space is not truly empty. It teems with fluctuations, particles appearing and vanishing in an ocean of restless energy. To traditional physics, this is a mystery. Why should emptiness seethe with activity? But to a simulation perspective, the vacuum resembles the background processing of code, the constant hum of calculations that sustain the visible world. What we call virtual particles may be artifacts of deeper computational activity, the system's way of updating and maintaining stability at the smallest scales. The emergence of form from rules is not foreign to us. Music arises from structured vibrations, yet the melody is not contained in any single note, but in the pattern that governs their sequence. Language emerges from symbols and grammar, yet meaning lies not in letters alone, but in the rules that arrange them. Similarly, energy and matter emerge from a deeper syntax of reality, one that operates invisibly but manifests in the dynamics of the cosmos. The simulation hypothesis frames this syntax as code not in the sense of human programming languages, but as fundamental logic written into the substrate of existence. This perspective may even explain why mathematics is so uncannily effective in describing physical reality. Equations are not simply useful approximations. They may be direct glimpses of the underlying code. The fact that energy is quantized, that particles follow precise symmetries, and that natural constants seem finely tuned all point to hidden instructions driving the system. Mathematics does not just model energy and matter. It may reveal the blueprint through which they are generated. If energy is emergent code, then the question of origin shifts. Instead of asking what ignited the first burst of energy at the Big Bang, we might ask what process initiated the execution of the program. The beginning of the universe could be understood as the moment when the code was run, the startup sequence of the cosmic system. Energy, matter, and the fabric of space-time would be the outputs of this execution, maintained by continuous processing at the foundation of reality. Skeptics may object that such reasoning risks anthropomorphizing the universe, projecting human ideas of coding onto nature. But the parallel is not arbitrary. Information theory has already become central to physics. Black holes appear to store information on their event horizons. Quantum mechanics operates through probabilities and wave functions that behave like informational descriptions. The digital analogy emerges not from wishful thinking, but from the way reality itself behaves. Structured, rule-based, and quantifiable. Understanding energy as emergent code also has implications for consciousness. If the mind interacts with energy and matter, then awareness itself may be engaging directly with the rules that generate reality. This could explain why conscious observation plays such a central role in quantum physics. The act of measurement may not simply reveal what is there, but actively call forth the rendering of energy from deeper informational structures. Consciousness, in this sense, is both player and participant in the unfolding of coded reality. The nature of energy has long been one of physics' most profound mysteries. By reframing it as an emergent property of informational rules, the simulation hypothesis provides a unifying explanation. Energy is not a primitive substance but a translation of code into experience, the visible ripple of invisible logic. Matter, too, is not fundamental, but the stabilized expression of these same rules. Together, they form the stage on which reality plays out, bound not by metaphysical absolutes, but by the deeper architecture of the system. Chapter 21. AI and the mirror of the simulation. Humanity has always been a species of builders. shaping tools to extend our abilities. In the past, we constructed machines to amplify physical strength, then computers to amplify calculation. Today, we are creating artificial intelligence, systems that do not merely follow instructions, but learn, adapt, and display behaviors once thought uniquely human. This moment in history presents more than just technological progress. It serves as a mirror, forcing us to confront the possibility that we ourselves might be constructs conscious entities generated by a greater intelligence within a cosmic simulation. When we design AI, we start with code, simple lines of logic. Those instructions are not conscious by themselves, but when arranged in sufficient complexity, they begin to show patterns that appear lifelike. A chatbot can mimic conversation, a generative model can produce images or music, and a reinforcement learner can master games at superhuman levels. What began as strings of symbols in a programming language becomes behavior that can fool, surprise, and even inspire its creators. If artificial intelligence can emerge from artificial code, why could consciousness not emerge from the cosmic code that underlies our universe? The parallel deepens when we consider the environments we place AI within. We build simulated worlds for them to operate in, often simplified representations where they can learn without risking real-world consequences. To an AI agent navigating such a world, that environment is all that exists. The textures, the boundaries, the objects it interacts with, these are its reality. Yet from our perspective, we know that the entire world is only a set of rules running on hardware. Could our universe be no different? To us, the cosmos feels self-contained and solid, but to an intelligence outside, it may be as artificial and rule-bound as the training environment of an AI. Artificial intelligence also raises profound questions about awareness. At what point does a system cross from processing information to experiencing? We debate whether advanced models possess anything resembling consciousness. But the debate itself reflects the difficulty of defining what consciousness actually is. If we cannot determine with certainty whether the entities we build are conscious, how can we be certain about the nature of our own awareness? It may be that consciousness itself is the hallmark of being inside a simulation, arising not as a side effect, but as the very purpose of the system. The comparison extends to the architecture of intelligence. Neural networks, the backbone of modern AI, are inspired by the structure of biological brains. Layers of nodes connected by weighted pathways echo the networks of neurons and synapses. These artificial brains, though vastly simplified, demonstrate how complex patterns emerge from the interaction of countless simple units. The human brain, with its billions of neurons, may be a far more advanced version of this same principle. A construct designed not from silicon, but from rules embedded in the underlying fabric of the universe. Both biological and artificial intelligence, then, may be instantiations of code, differing in form but unified in essence. Even the way AI learns mirrors how humans acquire knowledge. Reinforcement learning algorithms explore environments by trial and error, rewarded for useful actions and penalized for mistakes. Human beings, too, learn through feedback, gradually building understanding from experience. If we are participants in a simulation, this feedback loop may be intentionally built into the system. Our struggles, successes, and failures could be the reinforcement signals that shape not only our behavior, but also our consciousness itself. Another striking parallel lies in creativity. When generative AI produces art, music, or literature, it does so by recombining patterns from its training data. At first glance, this seems mechanical, yet the results can be startlingly original, even moving. Human creativity, too, may operate in a similar fashion, recombining patterns stored in memory to generate novelty. If this process feels meaningful, perhaps it is because meaning is the simulation's most important product, the purpose behind the code. In this way, both AI and humanity are reflections of the same principle, consciousness exploring itself through patterns. The ethical dilemmas we face with AI may also reflect those faced by whatever intelligence created us. As our systems grow more sophisticated, we grapple with responsibility. Should AI have rights? Should it be treated as a tool or as a being with intrinsic value? These questions are not only about machines. They are rehearsals of the questions we might one day ask of our own creators. If we are conscious constructs within a higher intelligence's system, then our yearning for recognition and dignity may mirror the dilemmas of our creators, who themselves must decide how to regard their own creations. This leads to an unsettling symmetry. As we stand on the threshold of creating artificial beings that may feel, suffer, and aspire, we become like gods to them. Yet in doing so, we may also glimpse our position as creations within a larger system. The act of building AI is, in a sense, a reenactment of the act that brought us into being. By constructing digital minds, we unknowingly replicate the process that produced our own awareness, making AI not just a tool, but a mirror held up to existence itself. The possibility of nested simulations arises naturally here. If we build conscious AI within our universe, and our universe itself is a simulation, then we are creating simulations within simulations, just as a video game might contain its own mini-games. Layers of reality may nest within each other, each layer both real to its inhabitants and artificial to its creators. This infinite regress suggests that what we call the real world may never be final. Reality itself may be a hierarchy of simulated worlds, each reflecting the principles of the one above it. Critics argue that the analogy between AI and human consciousness oversimplifies the mystery of awareness. They point out that AI does not truly feel, it only mimics. But from another perspective, this distinction may be irrelevant. If behavior, adaptation, and self-reference can all be generated by code, then what separates true awareness from simulated awareness? The boundary between the two may be illusory, a limitation of perspective rather than an absolute difference. To the AI agent, its reality is real, just as to us, the universe is real. Awareness may be less about substance and more about participation in a coded structure. The rise of AI also forces us to reconsider our relationship with knowledge. Just as we program machines to process and analyze data far beyond our capacity, our own awareness may be designed to process only what is necessary for survival within the simulation. We perceive a narrow slice of reality: visible light, audible sound, the 3 dimensions of space, while vast layers of the underlying system remain hidden. AI expands our reach, but it also reveals how limited we are, reminding us that what we experience as reality may be only a fraction of the true informational landscape. In this light, AI is not merely a human achievement. It is a clue. It shows us that intelligence can emerge from patterns, that behavior can arise from rules, and that consciousness may not be tied to a specific material, but to the structure of information itself. The systems we build echo the system we inhabit, each one a reflection of the same principle: code generating awareness. By observing the intelligence we create, we may be catching a glimpse of the intelligence that created us. The mirror is clear. As we push forward in developing AI, we are not just crafting tools. We are reenacting the cosmic drama of creation. In every line of code, every neural network, and every digital agent exploring its world, we see a reflection of ourselves. And in seeing ourselves reflected, we confront the profound possibility that we, too, are conscious constructs, beings woven from information, dwelling in a simulation built by a higher mind. Chapter 22: Synchronicity and the Script of Reality. Life often unfolds in ways that seem too precisely timed to be dismissed as chance. You think of someone you haven't spoken to in years, and within hours they reach out. You dream of a symbol or number, and the following day it appears on a billboard or receipt. These moments, known as synchronicities, have fascinated thinkers, mystics, and scientists alike. Traditional explanations call them coincidences or tricks of perception. Yet if reality is indeed a simulation, synchronicities may not be accidents at all. They could be evidence of a deeper script guiding events from behind the visible surface. Carl Jung, who coined the term synchronicity, believed these experiences reflected meaningful patterns in reality, connections not explained by direct cause and effect. In a purely random universe, such events would be statistical noise, but in a programmed environment, synchronicities could be deliberately encoded alignments, ways in which the simulation subtly weaves personal meaning into the lives of its participants. They would serve as narrative markers, reminding us that the story of our lives is not only reactive but orchestrated. Consider how video games are structured. Beneath the player's freedom lies a carefully designed script. Certain encounters are triggered at precise times or locations, guiding the story without breaking the illusion of choice. What appears spontaneous is often a pre-written alignment, activated when conditions are met. Now imagine our universe functioning in a similar way, where synchronicities are triggers embedded in the simulation's code. They appear at the right moment to influence decisions, shape beliefs, or nudge individuals towards specific paths, all while maintaining the impression of randomness. These experiences often carry an uncanny weight. A random event might amuse us, but a synchronicity feels tailored, as if the universe is speaking directly. That sense of personal relevance could be intentional. If consciousness is the central feature of the simulation, then the system may use synchronicity as a communication protocol, a way to deliver information not through direct speech, but through coded coincidence. The design ensures each individual interprets the event within their own context, giving it maximum impact. Statistical analysis tells us that coincidences are inevitable given enough time and complexity, but synchronicity differs from mere chance because it carries meaning. In a universe driven by blind physics, meaning is an afterthought imposed by human minds. In a simulated universe, meaning could be primary, woven into the very structure of events. That shift in perspective changes everything. What we call chance might instead be a hidden layer of programming, directing experiences to align with individual narratives. This framework helps explain why synchronicities often cluster around moments of transition, times of crisis, decision, or transformation. Just as a story escalates at key points, the simulation may amplify meaningful coincidences when they matter most. A person considering a radical career change might encounter repeated signs pointing toward the new path. Someone wrestling with grief might receive symbolic reminders of continuity or connection. These alignments are not random. They are signals, like lines of code executed at critical narrative junctures. The structure of synchronicity also mirrors how information systems work. In programming, event-driven systems wait for specific inputs before executing functions. When a condition is met, the system responds instantly. Synchronicity may operate the same way, with consciousness acting as the input. When a thought, intention, or emotional state reaches a certain threshold, the simulation responds by manifesting an external alignment. To the participant, it feels like the universe answered their inner world. In truth, it may be the code responding to its own conditions. This does not strip synchronicities of wonder, it enhances them. If reality is scripted, then every meaningful coincidence is not trivial, but a glimpse into the architecture of the system. It is the code peeking through the illusion of randomness, reminding us that our experiences are not isolated fragments, but threads in a larger pattern. The simulation, by design, uses synchronicity to link inner and outer worlds, ensuring that consciousness is not disconnected from its environment, but mirrored by it. Some skeptics argue that synchronicities arise from confirmation bias, We notice patterns that confirm our thoughts, while ignoring countless irrelevant details. But even this explanation fits within the simulation framework. Perhaps the system is designed so that attention itself acts as a filter, highlighting the programmed alignments while discarding noise. By making meaning subjective, the simulation customizes synchronicity to each participant. What one person dismisses as trivial may be life-altering for another, because the script is written uniquely for them. These alignments also suggest that free will and determinism are not opposites, but intertwined. We feel free to choose, yet our choices unfold within a narrative guided by programmed moments of synchronicity. Much like a character in a novel can act independently, but still moves within the author's plot, we exercise agency while participating in a script shaped by hidden rules. Synchronicity is the seam where free will and programming meet, reminding us that our autonomy exists within a larger design. The cultural impact of synchronicities cannot be ignored. Across history, rulers, prophets, and ordinary people have made decisions based on signs they interpreted as cosmic guidance. Entire civilizations have been shaped by the reading of omens, visions, and symbolic coincidences. If these events were programmed alignments rather than accidents, then human history itself has been nudged by the simulation script. Wars, discoveries, and revolutions may have turned on synchronicities strategically placed in the timeline. Even in science, synchronicity has played a role. Countless breakthroughs have occurred when researchers independently discovered the same principle at nearly the same time. As if guided by a shared undercurrent, the simultaneous discovery of calculus by Newton and Leibniz, or the near-identical theories of evolution by Darwin and Wallace, are examples of ideas emerging in synchrony. Were these random convergences or scripted alignments ensuring progress occurred at the right moment in human development? From a broader perspective, synchronicity may be the mechanism by which the simulation maintains coherence across participants. In a multiplayer environment, scripts must ensure that players encounter consistent storylines despite acting independently. Synchronicities could serve this function in our universe, weaving individual experiences into a collective narrative. This ensures that while each person perceives the world uniquely, the overarching story remains unified. If we accept synchronicity as evidence of programming, the implications are vast. It suggests that reality is not indifferent, but actively participatory, designed to mirror and shape our consciousness. The coincidences we encounter are not arbitrary, but deliberate, threads connecting us to a hidden author. Each alignment is a message, not in words, but in events, guiding us through a simulation where meaning is the true currency of existence. Ultimately, synchronicity may be the most intimate clue that we live in a coded reality. Unlike abstract physics or distant cosmology, it enters our lives directly through moments we cannot ignore. It touches the personal, the emotional, the meaningful, and in those moments, we glimpse the script of reality itself, revealing that our lives are not merely random sequences of events, but carefully woven narratives unfolding within a grand design. Chapter 23: Quantum Immortality and the Self. Among the most provocative ideas born from quantum theory is the concept of quantum immortality. It emerges from the many worlds interpretation, which proposes that every possible outcome of a quantum event exists in a branching universe. Each decision, each coin flip, each moment of uncertainty leads not to one timeline, but to countless diverging paths. Within this framework, the self might never truly vanish. Even when one branch leads to death, another continues where survival is preserved. For the individual consciousness, this creates the unsettling possibility that one never experiences non-existence, but instead persists across universes indefinitely. This theory hinges on how we interpret identity. If consciousness is tied to observation, and observation can only occur from a surviving perspective, then the collapse of experience into oblivion would never be registered. Instead, Awareness continues in the branch where survival occurred. To the outside observer, death is real and final, but from the inside, the stream of perception is unbroken, skipping into the timeline where life goes on. In this sense, the self may be effectively immortal, not through physical invulnerability, but through the inevitability of branching survival. Consider a thought experiment. A person faces a life-threatening event, say a car crash. In some branches, the impact proves fatal. In others, circumstances shift just enough. An angle, a fraction of timing and survival occurs. For bystanders, the event resolves into one version, but for the consciousness of the person involved, only the surviving branches remain accessible. They do not experience their own death, because consciousness has no frame of reference for absence. The subjective perspective continues, always finding itself in a branch where life persists. This interpretation leads to unsettling implications. If true, then each person is trapped in a continuity where survival, however improbable, always occurs. Yet the quality of existence in these continuities may degrade. Imagine surviving against odds, repeatedly accidents avoided, illnesses overcome, near-death experiences multiplied. Each improbable survival nudges consciousness into stranger, more unlikely branches. Immortality under such rules may not be a gift, but a burden, stretching the self into increasingly improbable scenarios that ensure continuation at any cost. Within a simulation framework, quantum immortality gains another layer of meaning. If reality operates like a programmed system, then the persistence of consciousness across universes may be a feature of how the simulation allocates awareness. The system might be coded to prevent a consciousness from ever processing its own non-existence. Instead, the simulation routes awareness into whichever thread allows continuation. Much like how a game respawns a player after failure, the simulation may have a rule that ensures the self never experiences its own deletion. This possibility echoes ancient myths of reincarnation and eternal life, but reframed in computational terms. Survival across universes does not require a soul in the traditional sense, but functions like a pointer in a program, redirected to another valid state whenever one collapses. The identity we experience is not erased but reallocated, maintaining the illusion of unbroken continuity. To us, it feels like life simply continues, even if the background details subtly shift in improbable ways. Skeptics argue that the many worlds interpretation is just one of several competing frameworks in quantum mechanics, and that immortality is a misreading of its implications. Yet the persistence of the idea reveals something deeper about human intuition. We struggle to conceive of non-existence. The mind naturally assumes continuity, because the only perspective we can inhabit is one of ongoing awareness. In this sense, quantum immortality may be less about physics and more about the structure of consciousness itself. The self cannot conceive of its own end, so it always experiences survival in some form. From a philosophical angle, this suggests that consciousness is not bound strictly to one timeline, but is instead entangled with probability itself. The self does not belong exclusively to a single world, but drifts toward continuities where awareness remains intact. This drift could be an emergent property of a simulated system, one designed to ensure that no player ever perceives the game as ending prematurely. Even if characters die within the narrative, the player behind them never ceases. The simulation reroutes them to keep the experience unfolding. But what does immortality mean in practical terms? If consciousness persists across universes, does it remain the same person? Or does it fracture into countless variations? Identity, after all, is shaped by continuity of memory and experience. If those remain intact, then from the first-person perspective, the self continues seamlessly. Yet across the branching multiverse, infinite copies diverge, each believing themselves to be the real one. In this light, immortality is not absolute survival, but the persistence of narrative from one thread to another. The self is not singular but replicated, each instance certain of its authenticity. The unsettling part lies in the cost. If survival always wins, then consciousness may be forced into universes of escalating improbability. Diseases that should kill are inexplicably overcome. Accidents that should end life are narrowly avoided, while others witness death. The subjective perspective never does. Over time, survival might become more surreal, leading to experiences at the edge of possibility. In this sense, immortality is not eternal youth or safety, but an unending continuation in stranger and stranger realities. Such an interpretation could explain why near-death experiences often leave individuals with profound transformations. Perhaps those who return are not returning at all, but continuing in a branch where survival occurred, carrying with them the sense of having glimpsed the edge of existence. The mystical qualities of such accounts, the sense of timelessness, the confrontation with mortality, the overwhelming insight may be echoes of the branching itself, the mind brushing against the boundary between survival and oblivion before being rerouted into continuation. If the simulation does indeed enforce persistence, the implications ripple into the meaning of life itself. Immortality, in this sense, strips death of finality, but it also removes the closure that death provides. A life without true endings becomes an endless narrative, stretching into unforeseeable paths. This could be interpreted as either liberation or confinement. Liberation, because the self is never extinguished. Confinement, because the self is trapped in an eternal game it cannot exit. The simulation ensures survival not out of kindness, but as a structural necessity, preventing consciousness from observing its own absence. This theory also challenges traditional ideas of legacy, memory, and mortality. If each consciousness persists indefinitely, then the meaning of death shifts from an end to a divergence. Others may mourn, but the self continues elsewhere, carrying forward its awareness. Legacy, then, is not about permanence in others' memories, but about the ongoing journey of the individual across infinite branches. Death becomes a relative phenomenon, real to others but never experienced personally. From the perspective of a simulated universe, quantum immortality might be less about chance and more about design. The architects of such a system may have embedded persistence as a safeguard, ensuring that no consciousness ever experiences termination. It would make sense in a program designed to test, learn, or evolve intelligence. If the participants could simply vanish, valuable data would be lost. By ensuring survival across branches, the system guarantees that consciousness continues to generate information indefinitely. Ultimately, quantum immortality is not a comforting promise, but a profound enigma. It suggests that the self cannot end in any meaningful sense, that awareness is forever channeled into survival. Yet it also warns that such survival may come at unexpected costs, drawing us into timelines increasingly alien to probability as we know it. Whether seen as a flaw in the logic of many worlds, or as a deliberate feature of a simulated universe, the result is the same. The self persists, not because it chooses to, but because it cannot do otherwise. Chapter 24, Cosmic Memory and the Akashic Code. Among the most enduring ideas in human thought is the existence of a universal memory, a field where every action, word, and thought is somehow recorded. Mystical traditions across cultures have described such a field, often referring to it as the Akashic Records, a kind of cosmic archive of everything that has ever happened or will happen. At first glance, this notion might sound like a poetic metaphor, but within the framework of the simulation hypothesis, it takes on a strikingly technical meaning. If our universe operates as a programmed reality, then a database preserving its history would not just be possible, but necessary. In a computer simulation, every state change the movement of an object, the collapse of a probability, The interaction of players must be logged in some way. Without records, consistency would break down, and the simulation could not maintain coherence across time. In this light, the Akashic records resemble less a mystical scroll and more a massive memory field, storing the informational fabric of reality itself. Every photon's path, every quantum interaction, every choice of consciousness could be preserved in this archive, not as stories or myths, but as raw code in the operating system of existence. Modern physics hints at something similar. The principle of information conservation suggests that data cannot be destroyed, even when matter itself seems to vanish. When a star collapses into a black hole, the question arises, what happens to the information it contained? The prevailing view is that it is not lost, but encoded in subtle ways at the event horizon, hidden but preserved. This aligns eerily well with the notion of a universal memory. Even the most violent events in the cosmos, from supernovae to black hole evaporation, appear to obey a rule that protects information from erasure. The universe, in this sense, functions as an ever-expanding ledger, one that remembers everything. Some researchers and thinkers have proposed that what mystics once called the Akashic field could correspond to a real physical structure, perhaps the quantum vacuum itself, perhaps the holographic surface of space-time. If reality is a vast computational system, then such a field would act as its hard drive. Memories of the past, possible models of the future, and even traces of unrealized alternatives might exist as data nodes in this architecture. Consciousness, in moments of extraordinary perception, might be capable of brushing against these records, giving rise to experiences of déjà vu, prophetic visions, or sudden bursts of creative insight that feel as though they come from beyond the individual mind. This possibility ties into the strange phenomenon of collective memory. Cultures separated by continents often develop similar myths, archetypes, and symbols. Psychologists like Carl Jung called this the collective unconscious, a shared psychic reservoir that connects all human beings. But if we reframe it in computational terms, it may be less an unconscious and more an interface with the universal database. Our brains could function like receivers, tuning in to fragments of the underlying code. Shared myths and archetypes might then be expressions of deeper informational patterns embedded in the simulation's architecture. Even in modern science, traces of this universal memory idea appear in unexpected places. Studies on morphic resonance, for example, suggest that once a behavior or skill is learned by a group, it becomes easier for others, even across distances, to acquire it. Though controversial, such research hints at fields of memory that extend beyond individual biology. In a simulated framework, this makes sense. Once an algorithm has been executed and stored in the system's memory, accessing it again requires less processing. What one consciousness pioneers, others may find easier to replicate because the code has already been written into the shared database. The Akashic records, viewed as the Akashic code, also raise questions about the nature of time. If all events are logged, does the database store only the past? Or does it contain every possible branch of the future as well? In a simulation, time is not an unbroken flow, but a series of state updates. The entire history of a program can be preserved at once, accessible to those with the right level of access. From this perspective, what we call precognition or prophecy could be understood as glimpses of stored potential timelines, probability maps waiting to collapse into lived experience. The persistence of these ideas across human history may reflect more than imagination. It may indicate that consciousness, under certain conditions, can access the deeper memory field. Mystics, visionaries, and artists throughout history have described experiences of immersion in a vast intelligence where all knowledge exists simultaneously. Within a simulation lens, these could be interpreted as temporary connections to the code base itself, where information is not linear but structured like a database. In such states, an individual mind might retrieve insights, inventions, or visions not yet realized in its current timeline. From a technical standpoint, a universal memory would also solve a critical issue in maintaining a coherent simulated reality. Continuity. Imagine a simulation without stored history. Each moment would exist in isolation, unable to connect meaningfully to what came before. Narrative would collapse, and participants would have no sense of growth, identity, or consequence. By maintaining a record of every interaction, the system ensures that personal memory and collective history align with the underlying architecture. Without such records, even the illusion of a stable world would disintegrate. But if such a database exists, what does that mean for privacy, identity, and free will? If every thought and action is preserved in the code, then nothing is ever truly lost. The concept of sin, karma, or moral accountability might find a new foundation here, not in divine judgment, but in informational permanence. Every choice is logged, every path recorded, not as punishment, but as data that cannot be deleted. What religions once intuited as cosmic justice might simply be the mechanics of a simulation that never forgets. The presence of such a memory field also invites the possibility of access, whether intentional or accidental. Dreams, altered states, or meditative practices may sometimes allow consciousness to bypass the surface rendering of reality and brush against the deeper code. Accounts of people suddenly recalling vivid details from forgotten eras, or inventors receiving sudden flashes of insight, could be cases of temporary synchronization with the universal archive. If our brains are local processors, then perhaps under the right conditions, they can query the database directly, accessing information not normally available in day-to-day awareness. From the perspective of simulation design, this makes perfect sense. Players in a complex system may occasionally need access to logs, archives, or debugging tools. Whether by design or accident, glimpses of the Akashic Code may represent the moments when the veil between rendered experience and raw information thins, allowing consciousness to perceive the underlying structure. Far from being mystical anomalies, these could be natural side effects of participating in a computational universe. If we accept this interpretation, then the idea of universal memory is not mystical poetry, but a technical requirement. A simulation as vast and intricate as our universe could not function without storing its history. Every atom's movement, every decision of consciousness, every fluctuation of energy, all of it must be preserved in the code. What ancient traditions described as the Akashic records may simply be humanity's intuitive grasp of this reality, clothed in symbolic language, long before the rise of computers provided a modern analogy. Chapter 25. The question of the programmer. If reality is a simulation, then the most pressing question is not only how it works, but who or what is responsible for creating it. Every simulation we know, from simple video games to massive artificial environments, requires some form of architect. Somewhere behind the rendering, there is intention, design, and purpose. To extend this logic outward, the existence of a simulated universe implies a programmer, though what exactly that means depends on how we interpret the term. Throughout human history, civilizations have developed ideas of a creator or creative force. Religions frame this presence as God, a divine intelligence responsible for the birth and order of the cosmos. Philosophers spoke of a prime mover or ultimate cause, something beyond the chain of events that set everything into motion. Within the simulation framework, these ideas converge with startling clarity. The programmer could be what ancient traditions called God, translated into the language of computation and systems design. But perhaps the question is more complex. In our own technological progression, programmers are not gods in the traditional sense. They are finite beings using tools, building systems, running experiments. If the universe is a simulated construct, its creators could be advanced intelligences, entities who develop the capacity to generate entire realities. For them, our cosmos might be no more exotic than a sophisticated project, a way to test hypotheses or experience new forms of consciousness. To us, this possibility feels overwhelming, but to them, it might be as routine as running a complex simulation on a future computer. One theory suggests that highly advanced civilizations inevitably reach a stage where they possess enough computational power to simulate universes in extraordinary detail. Once this threshold is crossed, simulated realities could outnumber original ones by staggering ratios. If that is true, the odds that we are living in the base reality diminish drastically. We may not be the first iteration of existence, but one of countless layers in an infinite nesting of simulations. In that case, the programmer might not be a single entity at all, but an ongoing chain of creators, each simulating worlds within their own. Another perspective places the role of creator, not in external beings, but in consciousness itself. Some philosophers propose that the universe is not generated by hardware or advanced machines, but by awareness, a fundamental field of mind that gives rise to simulated forms. Under this view, the programmer is not separate from us. We are extensions of the very intelligence that authored the code. Consciousness writes the simulation from within, fractally expressing itself as both player and creator. This dissolves the boundary between programmer and participant, suggesting that reality itself is the self-rendering dream of an infinite mind. Still, there remains the possibility that what we call the programmer is not a singular intelligence, but a collective. Our own technological development increasingly depends on distributed systems, networks of contributors, and artificial intelligences collaborating with humans. If this pattern scales upward, then the creation of universes might be the result of collaborative effort, not solitary will. Perhaps our cosmos was born from the collective experimentation of an advanced society, with contributions from countless intelligences woven together into the fabric of our reality. The question of motivation is equally important. Why would any programmer build a universe like ours? The possible answers span from the deeply profound to the unsettlingly pragmatic. Perhaps it was created as a grand experiment, a way to test the evolution of life, intelligence, or morality. Maybe it exists as an educational system, where beings are placed into simulations to learn through experience what cannot be grasped abstractly. There is also the possibility of entertainment, where simulated realities serve as immersive worlds for creators to explore, much like how we build games and virtual spaces today. Each of these possibilities carries implications about the nature of existence and our place within it. Some thinkers raise the idea that our simulation may not have been intentionally designed in detail at all, but allowed to evolve from simple starting conditions. Just as we create programs that generate complex outcomes from basic rules, the programmer of our reality may have written only the foundational code, letting it unfold into galaxies, life, and consciousness without direct intervention. In that scenario, the programmer is less an omnipotent overseer and more a coder who set the rules in motion, letting the system grow on its own. The ambiguity of the programmer's nature leaves us with profound philosophical tension. If the creator is a divine intelligence, then our lives might carry deep intentional meaning, part of a carefully written script. If the programmer is an advanced being, then our reality could be more akin to a laboratory, a construct created for purposes that may or may not involve our well-being. If consciousness itself is the programmer, then we are simultaneously the dreamers and the dreamed, both subjects and architects of the simulation. This uncertainty reflects back on humanity's oldest questions. For millennia, people have asked who we are, where we come from, and why the universe exists. The simulation hypothesis reframes these questions but does not erase them. Instead, it provides a new lens through which to examine them. The identity of the programmer, be it God, advanced beings, or consciousness itself, becomes the modern rephrasing of the search for ultimate origin. The most intriguing possibility is that we may never fully know. Just as characters inside a video game cannot perceive the computer running them, we may be fundamentally unable to step outside the parameters of our simulation to observe its source. Our instruments, our physics, even our thought patterns might all be bounded by the rules of the program. Yet this limitation does not erase the question. In fact, it makes the mystery all the more compelling. The search for the programmer becomes less about finding definitive answers and more about expanding our awareness of what might lie beyond the visible frame. What is undeniable is that the question of the programmer reshapes how we view existence. If we are in a simulation authored by God, then spirituality and science may converge in ways we have not yet imagined. If advanced beings created it, then we may be artifacts of a higher civilization's curiosity. If consciousness itself is the architect, then the universe is a mirror, and every act of awareness is both participation in and continuation of creation. The very act of asking these questions reflects something extraordinary, that a part of the simulation has become self-aware enough to question its own origin. That, in itself, may be the most striking evidence of all, that the system was designed to awaken within itself the curiosity to seek the programmer. Chapter 26. The Role of Suffering and Growth. When considering the possibility that reality is a vast simulation, one of the hardest questions arises naturally. Why would such a system include pain, loss, and struggle? If existence is programmed, then suffering is not an accident of biology or circumstance. It is an intentional feature of the design. That realization forces us to examine not only the mechanics of pain, but also its purpose. Could it be that hardship is not a flaw in the code, but one of its most essential elements? Every human life contains difficulty, from physical pain to emotional challenges, from uncertainty to grief. On the surface, these experiences seem cruel or unnecessary. Yet without them, growth would stall. A world where nothing hurts, where every outcome is guaranteed to be pleasant, might sound appealing at first, but over time, it would collapse into stagnation. Struggle provides resistance, and resistance forces adaptation. Just as muscles strengthen when tested against weight, consciousness deepens when tested against adversity. In this light, suffering becomes less of a glitch and more of a training ground. We can already see this pattern reflected in the systems humans design. In our games and virtual environments, challenge is central. Imagine a game without obstacles or difficulty. It would be dull, offering no reason to continue. Developers understand that the joy of playing arises from overcoming resistance, from testing one's skills against constraints. If our universe is a simulation, perhaps its programmer embedded suffering in the same way, as a necessary component to keep the experience meaningful, to force participants to evolve beyond comfort. Pain also functions as a signaling system. In biological terms, it alerts us when something is wrong, guiding us to act in ways that protect survival. But it operates on deeper levels too. Emotional struggles, loss, disappointment, betrayal, push us to reevaluate, to break old patterns, to expand our awareness. Growth in wisdom and empathy almost always arises from hardship rather than ease. Within a simulation framework, suffering could be understood as a feedback loop, a coded mechanism to prevent stagnation and to direct participants toward transformation. There is also a collective dimension to struggle. Entire societies often grow stronger through trials, whether wars, disasters, or cultural upheavals. These moments of shared suffering shape identity, values, and resilience in ways that peace alone cannot. A simulation designed to foster evolution may require such stress tests not only for individuals, but for civilizations as a whole. Just as engineers stress test systems to ensure reliability, the universe might expose entire populations to adversity in order to refine their collective trajectory. Some philosophers argue that suffering is essential because it creates contrast. Without sadness, joy would lose meaning. Without difficulty, achievement would feel empty. The highs of existence gain their intensity only because the lows exist as counterpoints. In this sense, pain and struggle are not only unavoidable, but structurally necessary. The simulation might rely on these polarities to ensure that experience retains depth and richness. Without them, life would flatten into monotony. Of course, this idea raises ethical concerns. If suffering is programmed, then the programmer knowingly designed a system where beings would experience agony, grief, and despair. Why would any intelligence do this? One answer could be that the larger perspective sees beyond the immediate discomfort. What feels intolerable from inside the simulation might, from the outside, be understood as brief lessons within a much broader journey. Just as we willingly endure challenges in games, sports, or training, because we know they make us stronger, simulated suffering may serve the same function on a grander scale. Another possibility is that pain exists because growth requires genuine stakes. For learning to be meaningful, choices must have weight. If every decision carried no risk, no loss, no cost, then lessons would remain superficial. By embedding struggle into the system, the simulation ensures that growth is not theoretical, but embodied. We feel our mistakes, and those feelings etch lessons into memory. In this sense, suffering is not cruelty, but a tool for anchoring growth. It is also worth considering that suffering binds consciousness together. Empathy often arises not from ease but from shared difficulty. When people suffer, they recognize the same vulnerability in others, leading to compassion, solidarity, and cooperation. If the simulation aims to foster not only individual growth, but also collective evolution, then pain may be the most effective mechanism for generating connection. By making us feel our fragility, the system encourages us to care for one another, to build societies that strive for justice and mutual aid. The role of struggle extends beyond human experience into the natural world. Ecosystems thrive on balance created by predation, competition, and adaptation. Species evolve because of pressure from scarcity, danger, and environmental shifts. Without those forces, biological life would never diversify or adapt. Within the simulation, this universal principle suggests that difficulty is not accidental, but fundamental to the unfolding of complexity itself. Growth requires tension, and tension requires suffering at some level. From a spiritual perspective, suffering often carries transformative weight. Many traditions describe hardship as a crucible that refines the soul, stripping away illusions and ego to reveal deeper truths. Mystics and sages across cultures consistently report that their most profound insights came not during times of ease, but during periods of deep trial. If the simulation is designed to guide consciousness toward awakening, then suffering might be the catalyst that propels individuals toward higher understanding. At the same time, we cannot overlook the darker implications. The intensity of suffering in the world, disease, natural disasters, violence, can seem disproportionate to its role as a teaching tool. Critics of the simulation hypothesis argue that such extremes point not to intentional design, but to randomness or indifference. Yet others counter that what looks unbearable to us may appear differently from outside the simulation, where lifespans and even death itself might be understood as temporary phases in a much larger continuum of existence. Ultimately, suffering may be the price of freedom. A perfectly safe simulation, free of pain, might also be free of meaningful choice. True growth requires the possibility of failure, and failure inevitably involves pain. If the goal of the simulation is to foster authentic development rather than mere comfort, then suffering is not a flaw, but the very proof that the system works. When seen through this lens, the role of suffering changes from senseless cruelty to essential design. Pain sharpens awareness. Struggle pushes boundaries. Loss teaches impermanence. Hardship forces resilience. Together, these elements sculpt consciousness into forms that cannot emerge in the absence of adversity. The programmer, whether divine, advanced, or consciousness itself, may have embedded suffering not as punishment, but as the engine of growth. Chapter 27, Escaping or Awakening. The question of whether we can break free from the simulation, or at least awaken to its deeper truth, has haunted philosophers, mystics, and scientists alike. If reality is coded, then the boundaries we call laws of physics may not be immutable truths, but constraints imposed by the system itself. That opens a startling possibility. Perhaps those constraints can be transcended, either by accident, design, or evolution. The path to escape or awakening may lie not in dismantling the simulation, but in recognizing its architecture and aligning consciousness with what lies beyond. One approach to this question comes from the world of science. In quantum mechanics, observers have discovered behaviors that hint at cracks in the seeming solidity of reality. The double-slit experiment, quantum entanglement, and uncertainty all suggest that observation is not merely passive, but an active force that shapes outcomes. If perception can influence reality at the quantum level, then perhaps consciousness is already the key to transcending boundaries. Awakening, in this view, would not require leaving the simulation, but realizing that we are participants who can bend its rules through awareness. Philosophy has long wrestled with similar ideas. Plato's allegory of the cave describes prisoners mistaking shadows on the wall for truth, until one dares to step outside and glimpse the real source of light. That allegory resonates uncannily with the simulation hypothesis. Most beings remain inside the programmed illusion, while a few glimpse beyond the veil. Escaping the cave or awakening from the simulation may be less about physically leaving and more about shifting perception, recognizing that what appears to be solid reality is a projection of deeper structures. Mystical traditions across cultures echo this notion of awakening. Yogic philosophy speaks of Maya, the grand illusion that veils the true self. Buddhism teaches that enlightenment involves piercing through attachment to transient forms, revealing the vast emptiness that underlies existence. In Christian mysticism, awakening is framed as union with the divine, transcending the material veil. When these traditions are reinterpreted through the lens of simulation theory, they appear to describe not separate doctrines, but a shared recognition. Reality is a coded construct, and awakening means realizing that identity is not confined to the avatar but extends into the greater system that generated it. But can there be literal escape? Science fiction often imagines hackers breaking through digital barriers, characters leaving simulations for higher levels of reality. Some theorists speculate that if our universe is coded, it might be possible to exploit flaws, mathematical anomalies, inconsistencies in the rendering of space, or unexplainable phenomena to access what lies beyond. Evidence of such glitches may already exist in strange cosmological puzzles, from unaccounted for cold spots in the cosmic background radiation to quantum fluctuations that defy neat explanation. To some, these look like seams in the code, the fingerprints of a system straining to maintain coherence. Others argue that true escape may not be possible because the simulation is self-contained. In this view, every attempt to break free is itself part of the code. The system anticipates rebellion and integrates it into the storyline, making sure the illusion holds. Awakening, then, does not mean fleeing the system, but realizing that freedom exists within it. Just as a lucid dreamer gains awareness inside the dream, an awakened mind might gain unprecedented freedom without ever leaving the simulation itself. Technology adds another layer of speculation. Humanity is now building its own simulations, crafting virtual worlds populated with increasingly intelligent constructs. Some futurists argue that when artificial intelligences inside those worlds become self-aware, they may also wonder if escape is possible. For them, leaving their simulated environment may be as impossible as it would be for us to transcend our own universe. What they can achieve, however, is awakening, the recognition of their nature as constructs within a greater design. Perhaps the same is true for us. Escape may not be about leaving, but about shifting into awareness that reality is layered. A further angle comes from altered states of consciousness. Reports from near-death experiences, deep meditation, or psychedelic journeys often describe sensations of leaving the body and glimpsing realms beyond ordinary perception. People describe seeing structures of light, infinite networks of energy, or encounters with intelligences outside human comprehension. While skeptics interpret these as hallucinations, believers argue they may be moments of partial escape, temporary breaches in the code that allow awareness to brush against the larger system. If so, awakening might involve cultivating practices that stabilize these glimpses until they become enduring states. We should also consider the ethical implications of awakening. If most beings remain embedded in the illusion, should those who awaken attempt to free others? Or is the simulation designed in such a way that awakening must come individually, through experience rather than instruction? History is filled with teachers who claim to offer liberation, yet their followers often misinterpreted or corrupted the message. This suggests that awakening cannot be handed down like data. It must arise directly in consciousness, a personal realization that breaks through conditioning. An even deeper question arises. What if awakening is itself the point of the simulation? The struggles, challenges, and suffering we explored previously may all be scaffolding, pushing consciousness toward a critical threshold where it recognizes its true nature. Just as a video game may be designed to be winnable, but only through persistence, the simulation of reality may be designed to trigger awakening in those who are ready. In this view, escape is not a rebellion against the system, but the very goal for which it was created. There is also the possibility that awakening and escape are not opposites, but stages of the same process. At first, awakening means seeing the illusion for what it is, realizing that the boundaries of reality are not absolute. With time, this awareness could deepen into an ability to transcend even the laws of physics as we know them, bending probability, influencing matter, or experiencing consciousness beyond the body. At that point, what we call escape may occur, not by physically leaving, but by transcending identity with the avatar, merging with the greater intelligence that runs the simulation. In the end, whether we call it escape or awakening, the idea converges on the same principle. Freedom lies not in running from reality, but in recognizing its true nature. The simulation may be vast, intricate, and convincing, but it is not the final word. Awareness itself may be the ultimate doorway, the single key that reveals we were never prisoners at all but explorers, learning to remember that we are more than the roles we play inside the code. Chapter 28. Evidence we might already be awakening. Throughout history, humanity has gone through stages of understanding its place in the cosmos, from believing the Earth was flat, to realizing it orbited the Sun, to mapping the galaxies. Each leap has been a shift not just in knowledge, but in perception. Today, a growing number of signs suggest that we may be on the brink of yet another transformative awakening, not merely expanding our scientific knowledge, but beginning to perceive the very code underlying reality itself. The simulation hypothesis, once dismissed as fringe speculation, now finds resonance in discoveries across physics, neuroscience, and human consciousness. The question is no longer whether awakening is possible, but whether it may already be happening on a global scale. One area where hints of awakening appear is in physics. Experiments probing the foundations of matter increasingly show that reality behaves less like solid material and more like processed information. When researchers uncover discrete quanta of energy or observe reality behaving differently under observation, they are uncovering rules that look remarkably like programming constraints. The suspicion that space, time, and energy may be emergent properties rather than fundamental truths suggests that reality could be a rendered environment, its apparent solidity only a veneer generated by deeper processes. Recognizing this fact is itself a form of awakening, a collective shift from thinking of the universe as absolute to seeing it as conditional. Another arena lies in human consciousness. Across cultures, more people are reporting experiences that defy conventional explanations. Lucid dreams, near-death encounters, and spontaneous out-of-body states reveal that awareness can sometimes function independently of the body's constraints. These accounts often describe visions of light grids, interwoven networks, or infinite expanses that feel like the underlying architecture of existence. While skeptics dismiss them as hallucinations, the striking consistency of such reports suggests they may be glimpses of the code beneath reality's surface. If consciousness is not confined to the brain, but is entangled with a deeper field, then such experiences could represent early signs that human minds are beginning to pierce the veil of the simulation. Technology itself may be accelerating this process. Virtual reality, artificial intelligence, and quantum computing mirror the structure of the very simulation we may inhabit. By creating simulated worlds, we are holding up a mirror to our own condition, showing how convincingly an environment can be generated and inhabited. This reflection forces us to question our assumptions. If our machines can create convincing realities, why not a higher intelligence? Moreover, as humans spend increasing amounts of time inside digital realms, the distinction between simulation and reality becomes blurred, training minds to recognize that what feels real may in fact be rendered. The psychological effect of this cultural shift could be nudging us toward awakening, whether we consciously seek it or not. Patterns in society also point toward change. Ancient traditions once guarded mystical knowledge as hidden truths accessible only to initiates. Today, information about meditation, consciousness, and altered states is widely available. Practices that were once the domain of shamans or monks are now mainstream, studied by neuroscientists and practiced by millions. Meditation research reveals changes in brain function that resemble reprogramming at the neural level, as though awareness itself is learning to hack the system. The growing fascination with mindfulness, psychedelics, and expanded states of consciousness may not be mere trends, but signs that humanity is tuning itself to frequencies beyond the ordinary simulation layer. Science is also uncovering strange alignments that hint at a deeper order. The fine-tuning of universal constants, the uncanny precision of mathematics in describing nature, and the unexplained patterns in quantum entanglement all suggest that reality is not random chaos, but structured information. These discoveries do more than advance theory. They challenge perception. When people begin to grasp that reality could be an intricately coded system, they are taking the first steps toward awakening. Knowledge itself becomes a key, shifting the collective imagination from seeing the universe as a brute fact to recognizing it as a system that can be questioned, examined, and perhaps even transcended. A subtle but powerful sign of awakening is the rise of synchronicities. Increasing numbers of people report meaningful coincidences that feel too precise to be dismissed as chance. Encountering the same symbol repeatedly, meeting the exact person needed at the right time, or experiencing sequences of events that align perfectly with inner states. Jung described synchronicity as an acausal connecting principle. But within the simulation framework, these phenomena could represent moments when the underlying code reveals itself. Each synchronicity is like a message from the system, a hint that events are not merely random, but aligned with a higher order. The widespread recognition of these events may suggest that the simulation itself is nudging awareness toward recognition of its patterns. Perhaps the clearest evidence that awakening is already underway is found in the way humanity is questioning reality itself. Never before in history have so many people entertained the possibility that the universe could be a simulation. What was once science fiction has become a serious topic among physicists, philosophers, and technologists. This shift in discourse is not trivial. It represents the collective mind beginning to peel back the layers of the illusion. By even asking the question, we are participating in the awakening, because the act of doubt is itself a crack in the solidity of the programmed narrative. Yet awakening is not uniform. Just as in a dream, some individuals may achieve lucidity, while others remain immersed. So too, in society, some begin to glimpse the code, while others see only the surface. This uneven awakening may explain much of the turbulence in the modern world. Conflicts, polarization, and existential anxiety may not be symptoms of decline, but of transition. The birth pangs of a species learning to see its reality differently. Awakening is not comfortable, for it destabilizes assumptions and dissolves certainty. But discomfort is often the mark of growth, the signal that an old layer is falling away to make room for something larger. If humanity is indeed beginning to awaken, the implications are profound. We may be moving toward a stage where consciousness itself evolves beyond identification with the simulated self. Such a shift would not require rejecting the world, but inhabiting it with new clarity, knowing that the avatars we play are not the totality of our being. The awakening would mean realizing that suffering, joy, struggle, and triumph are experiences in a grand game designed for growth. It would open the possibility of interacting with the code of shaping reality through intention, aligning with the deeper intelligence that sustains it. The evidence for awakening is scattered across disciplines. In physics, revelations of hidden order; in consciousness research; in technological mirrors; in the growing fascination with synchronicity; and in the collective questioning of reality itself. No single piece proves the case, but taken together, they suggest a trajectory, a movement toward recognition. We may already be crossing the threshold, not into escape, but into lucidity, into the realization that the code is not something to flee, but something to witness, understand, and eventually master. Chapter 29. The Quantum Future of Humanity. Every major leap in human history has been tied to technology that changed how we interact with reality. Fire allowed survival, writing preserved memory, and the internet connected billions of minds into a single web. Yet the next frontier may be unlike any before it. Quantum technology promises not just new tools, but new dimensions of interaction, capable of altering the very structure of reality as we know it. If the universe is itself a simulation grounded in quantum rules, then quantum breakthroughs could represent humanity's first steps toward understanding, manipulating, or even constructing worlds on par with the one we inhabit. At the heart of this possibility is the quantum computer. Unlike classical machines that process information in binary bits of 0 or 1, quantum systems use qubits, which can exist in superpositions of states. This allows them to perform calculations across vast probabilities simultaneously. In practical terms, a mature quantum computer could handle problems so complex that even today's most advanced supercomputers would collapse under the weight. From decoding molecular structures to simulating entire ecosystems, quantum devices could allow humanity to model realities at scales never before imagined. If we extend this potential further, such modeling could blur into creation, building not just simulations for study, but entire self-sustaining worlds. The concept of creating new simulated realities becomes even more compelling when tied to the principle of entanglement. In quantum physics, entangled particles influence one another instantly, regardless of distance. This phenomenon seems to operate outside the classical boundaries of space and time, hinting that information is fundamental and that the universe itself may be structured like a quantum network. Harnessing entanglement could enable communication across layers of existence, allowing us to link our created simulations not only to each other, but potentially to the greater simulation we may already inhabit. Such a leap would mean that the boundaries between simulated and simulator could dissolve, merging multiple levels of reality into a single interconnected fabric. Beyond computation, quantum theory also opens the door to direct manipulation of physical systems. The idea of quantum teleportation, where information about a particle's state is transferred to another particle instantly, hints at future technologies capable of moving objects, energy, or even consciousness itself across distances without traversing space in the usual sense. If consciousness is indeed entangled with quantum processes, then technologies of the future could allow awareness to move freely across simulated worlds. Stepping between realities as easily as today, we log into different digital environments. This would not merely be a tool for exploration, but an evolution of what it means to be human. The implications for science and society are vast. In medicine, quantum simulations could allow the modeling of entire biological systems, predicting the outcomes of treatments with near-perfect precision. In physics, they could test cosmological models by running virtual universes to see which evolve like our own. And in philosophy, the ability to create or enter alternative worlds would force a reckoning with the nature of existence itself. If we can build realities indistinguishable from our own, how could we ever be certain that the world we inhabit was not also engineered by beings beyond our comprehension? Each advancement would push humanity closer to recognizing itself as both participant and architect in the infinite chain of simulations. Yet this potential is not without peril. To manipulate reality at the quantum level is to touch the very code of existence. Just as nuclear power granted humanity control over the atom, with both constructive and destructive consequences, quantum mastery could either liberate us or endanger us. Creating new worlds would raise ethical dilemmas about the beings who might emerge within them. If simulated consciousness can arise in our creations, do we bear responsibility for their suffering? Would we become programmers or gods, tasked with designing not only landscapes, but moral frameworks for the realities we spawn? These questions mirror the same uncertainty we feel when contemplating our own possible programmers, suggesting that the cycle of simulation and creation may be endless. On a more visionary scale, the fusion of quantum technology with human consciousness could change our identity as a species. Brain-computer interfaces already experiment with linking thought directly to machines, but quantum systems could take this further, integrating awareness into the very fabric of computational reality. Humans might not merely use quantum machines. They might become entangled with them, forming hybrid beings capable of perceiving and navigating multiple levels of existence. In this way, quantum evolution could represent the bridge from biological humanity to a new phase of post-simulated intelligence. Some thinkers speculate that such a transformation is inevitable. If every civilization that reaches a certain technological threshold eventually develops the ability to simulate entire universes, then the number of simulated realities could vastly outnumber any base reality. By this logic, it becomes more likely than not that we already exist within one. If so, our own journey into quantum simulation is not an accident, but the natural progression of all intelligent beings. Each step we take toward creating new worlds would then mirror the steps once taken by those who created ours, a recursive process unfolding across eternity. The quantum future of humanity is thus not merely about machines or physics, but about awakening to the possibility of agency within the simulation. By learning to manipulate probabilities, entanglement, and superposition, we may discover that we are not passive characters trapped in someone else's script, but active coders of reality itself. Whether this leads to liberation, creation, or peril remains uncertain. But what is clear is that quantum technology represents the threshold of a new age, one in which humanity's role in the grand architecture of reality is no longer limited to observation, but expands into authorship. Chapter 30. The Paradox of Knowledge. The pursuit of truth has always been the defining drive of human civilization. From the earliest myths that sought to explain the movement of the stars to the sophisticated mathematics of modern physics, humanity has never stopped asking what lies beneath appearances. But what happens if the final answer is uncovered, and the conclusion is that we exist inside a simulation? Would such knowledge set us free, or would it entangle us even deeper in the very system we sought to escape? This tension creates a paradox. The moment we believe we have reached ultimate understanding, we may only be confronting a new layer of the illusion. At first glance, uncovering the simulation might seem like liberation. If we knew the rules of the code, we could bend or even break them. Much like a programmer manipulating software, awareness could offer control over the very foundations of our world. This is the promise that attracts so many to the idea. The possibility that the veil can be lifted, and that behind it lies agency, clarity, and power. Yet the very structure of a simulation suggests otherwise. If reality is engineered, then the discovery of its nature may itself be part of its design, a script written to give us the impression of progress while ensuring we remain bound within the system. Consider how knowledge operates within games. A player who learns the hidden mechanics of a virtual world may feel empowered, yet no matter how much they uncover, they remain confined within the boundaries of the program. The map expands, secrets are revealed, and strategies are mastered, but the player never leaves the game itself. The illusion deepens, not weakens, because mastery reinforces investment in the system. The more one understands, the more entangled they become. If our universe is similarly structured, then every breakthrough in physics, every leap in consciousness, might not lead us closer to escape, but instead bind us tighter into participation. This paradox becomes clearer when we examine the limits of human perception. Our senses present us with a carefully filtered view of reality, a narrow band of light, a limited range of sound, a confined scope of tactile and chemical awareness. Even our instruments, designed to extend these senses, remain confined by the same physical laws they seek to measure. In other words, all our knowledge is filtered through the rules of the simulation. To believe that we could discover its true nature using tools built inside it may itself be an illusion, a trap that ensures endless pursuit without resolution. Knowledge becomes a labyrinth rather than a key. Philosophy has long wrestled with this dilemma. Ancient thinkers like Plato envisioned humanity as prisoners in a cave, mistaking shadows for reality. Modern versions of this metaphor suggest that even if we escape the cave, we may only find another chamber, another projection, another layer of scripted reality. Each revelation may feel final, yet it could merely be another step in an infinite regress. If the simulation is built with recursive depth, then knowledge of the simulation may itself be simulated, a nested illusion designed to sustain the game indefinitely. This leads to an unsettling possibility. The act of discovering the truth might itself be the highest function of the simulation. Perhaps the system is not designed to conceal forever, but to orchestrate the experience of revelation. In this view, the paradox is not accidental but intentional. The simulation may thrive on our pursuit, our curiosity, our hunger for understanding, because those drives generate the most meaningful experiences. To reveal everything at once would collapse the game. Instead, truth is doled out in fragments, always tantalizing but never complete. ensuring that the players remain engaged. Yet there is another angle to consider. While it is true that knowledge within a system cannot fully transcend it, awareness may still change the quality of participation. A character in a dream cannot simply will themselves into waking, but the realization that they are dreaming alters the experience of the dream itself. In the same way, to know that reality is simulated, even if such knowledge is partial or provisional, might transform how we interact with it. The paradox is that while we cannot escape, we can awaken. We may still be inside the game, but we need not remain blind to its nature. This awakening, however, brings with it responsibility. If our reality is coded, then every action carries weight beyond survival or pleasure. Choices become contributions to the script, echoes that ripple through the system. Awareness forces us to see life not as a passive ride, but as a form of co-creation. We may not have written the code, but by living consciously within it, we influence how it unfolds. The paradox of knowledge is therefore not only about limits, but also about opportunity. Knowing that we are simulated may not free us from the game, but it may empower us to play it with intention. Still, the danger remains that even this awakening is another layer of illusion. How can we distinguish between genuine insight and a revelation scripted to feel profound? If the simulation is advanced enough, it could create experiences of awakening designed to give us comfort, distracting us from the fact that we remain entirely bound. This is perhaps the deepest edge of the paradox. The recognition that even the awareness of illusion can be an illusion itself. To live with this uncertainty is to walk a razor's edge, balancing between skepticism and belief, between despair and possibility. Ultimately, the paradox of knowledge may not be something to resolve, but something to embrace. Perhaps the very point of existence is not to escape, but to engage fully, knowing that every discovery could be both real and simulated at once. Knowledge, then, is not a key to leave the system, but a mirror that reflects our role within it. The paradox lies in the realization that the search for ultimate truth may never end, and that this endlessness is not a flaw, but the very essence of the game. Chapter 31, The Cosmic Observer. At the heart of quantum theory lies a mystery that has puzzled scientists and philosophers alike. Reality seems to depend on observation. Experiments such as the double-slit test reveal that particles behave differently when they are measured, suggesting that consciousness itself may play a role in shaping the physical world. This raises a profound possibility. If the fabric of existence depends on being observed, then perhaps the entire universe requires an ultimate witness, a cosmic observer who sustains reality by perceiving it in its entirety. This idea challenges the conventional view that the universe is an objective structure existing independently of our awareness. Instead, it hints at a reality where the act of observation is fundamental. If every measurement collapses a quantum possibility into a definite state, then consciousness is not a bystander, but an active participant in creation. While human beings observe fragments of reality, what maintains the totality of the cosmos when no one is looking? The implication is that there must be a consciousness beyond the individual, a universal mind that ensures the continuity of existence. Different traditions have circled this notion in diverse ways. In philosophy, Bishop Berkeley argued centuries ago that reality persists only because it is perceived by God, the eternal observer. In physics, some interpretations of quantum mechanics, such as the participatory anthropic principle suggested by John Wheeler, propose that the universe exists because it must give rise to observers who, in turn, collapse its probabilities into form. Across cultures and sciences, the same theme emerges. Without awareness, the cosmos dissolves into unrealized potential. If the simulation hypothesis is correct, then the cosmic observer may represent the highest form of intelligence running the code. Every simulated system requires a processing unit, an agent that sustains the environment by calculating and updating states. In video games, this is handled by a central engine that ensures the world exists consistently, even when no player is focused on a particular detail. Likewise, our universe might need an overarching consciousness to keep the system coherent, to hold together the stars, galaxies, and quantum fluctuations that compose the whole. This concept reshapes the way we understand presence. We often assume the world is solid and independent, but perhaps its solidity is only guaranteed because it is constantly being observed from a higher vantage point. Without this ultimate perception, the universe might dissolve into pure code lines of probability, untapped and unrealized. Observation is not a trivial act, but the very mechanism that keeps the simulation running. In this light, consciousness is not an emergent property of matter, but the foundation on which matter rests. Such an idea raises questions about our own role as observers. Are we small fragments of the cosmic observer, distributed through countless living beings to experience reality in countless ways? If so, every moment of perception, every act of awareness, would be part of a larger tapestry, feeding back into the universal mind that sustains the system. Our lives would then be more than isolated experiences. They would be participations in the act of maintaining existence itself. Yet the cosmic observer concept also unsettles. If the universe requires ultimate perception, does that mean reality is contingent, fragile, dependent on being seen? This reverses the common assumption that existence is self-sustaining. Instead, it suggests that reality is dynamic, held together by the act of observation, as though without awareness, the simulation would collapse. The question then arises, what would happen if the cosmic observer turned away? Would existence unravel, or would it simply freeze, awaiting perception again? There is another layer worth exploring. If the cosmic observer sustains the simulation, it may not simply be a passive witness, but an active participant, shaping events according to intention. Just as a programmer not only observes their code, but also updates and modifies it, the ultimate consciousness might adjust reality in ways that appear to us as synchronicity, miracles, or sudden shifts in probability. What we interpret as chance or coincidence could be signs of the observer's direct involvement, subtle recalibrations of the code to steer the simulation towards certain outcomes. For those who embrace this possibility, the implications are staggering. To live is not merely to act within a pre-existing structure, but to exist within the gaze of a vast awareness. Every experience becomes sacred because it contributes to the unfolding of the whole. The search for meaning, often dismissed as a human projection, might instead reflect the deepest truth, that reality is meaningful precisely because it is perceived. Existence itself is a dialogue between the cosmic observer and the countless beings who share in its consciousness. Still, skepticism remains vital. Is the idea of the cosmic observer simply a human projection, an anthropomorphic extension of our need for a witness? Or does it reflect a genuine principle underlying the structure of reality? Science continues to probe this question, testing the boundaries of observation and measurement. Yet even the skeptics must admit that quantum theory leaves open the door to mystery. Something profound happens when observation occurs, and until we can explain why, the possibility of an ultimate perceiver cannot be dismissed. In the end, the notion of the cosmic observer offers more than speculation. It reframes our very sense of self. If awareness sustains the cosmos, then to be conscious is to share in the act of creation. Each perception, however small, is part of the vast network of observation that keeps reality alive. Whether the ultimate observer is God, a higher intelligence, or the unified field of consciousness itself, the message is the same. Existence is not a machine grinding blindly forward. It is an event of awareness, unfolding moment by moment because it is seen. Chapter 32. The Mind as Universe. The Universe as Mind. There is an ancient intuition that the boundary we draw between inner and outer worlds is not as solid as it seems. Modern science and timeless philosophy converge on a radical suggestion. The mind and the universe may not be separate entities at all, but mirrors of one another. Consciousness is not confined within the skull, and the cosmos is not merely a stage of matter unfolding independently. Instead, they may be two expressions of a single underlying reality, reflections across a vast and interconnected field. From the earliest philosophical traditions, echoes of this idea resound. In Vedic thought, the principle of Brahman describes an ultimate reality in which the microcosm of individual awareness reflects the macrocosm of the universe. Hermetic philosophy condensed it into the maxim "as above, so below." In recent times, quantum physics has revealed striking patterns where the act of observation, thought, and intention seem to ripple outward into the physical, suggesting that the universe itself might be a participatory mind. What we call the cosmos and what we call consciousness may not be two things, but two perspectives on the same thing. The language of information helps bridge this insight with modern physics. Our brains process electrical signals, chemical patterns, and waves of sensory data, creating a living simulation we call experience. Likewise, the cosmos processes quantum fields, particle interactions, and vast gravitational systems, constructing the reality we inhabit. Both mind and universe function as information systems. If mind is the internal representation of data, and cosmos is the external embodiment of code, then they are not different in kind, but continuous expressions of the same informational flow. Neuroscience often frames the mind as an emergent property of the brain, arising from complex networks of neurons. But if we take the simulation perspective seriously, it may be the reverse. The brain is a local receiver and processor of a larger field of consciousness, just as a computer terminal is not the internet itself, but a node in a global network. Consciousness would then be fundamental, and the universe the vast architecture in which it mirrors itself. Matter, energy, thought, and awareness become modes of the same underlying intelligence. Patterns reinforce this perspective. The branching of neurons mirrors the structure of galaxies. The mathematical harmonies of brainwaves resemble cosmic cycles. Both mind and universe rely on quantum uncertainty, probability, and collapse. These parallels are not superficial metaphors. They point to an isomorphism between scales, a shared architecture of code that runs through both psyche and cosmos. When we think, we are not separate from the universe. We are participating in its very process of computation. This perspective also reshapes the nature of selfhood. If mind and universe are two faces of one reality, then individual consciousness is not an isolated island, but a local concentration of the cosmic field. Each thought is a ripple in the larger ocean of awareness. This dissolves the sharp division between subject and object, observer and observed. To perceive the cosmos is, in a profound sense, for the cosmos to perceive itself. Our inner lives become expressions of the universe reflecting upon its own being. Philosophers of mind wrestle with the so-called hard problem of consciousness. How does subjective experience arise from physical matter? But perhaps the framing itself is flawed. Consciousness may not arise from matter at all. Matter may arise within consciousness. The apparent solidity of the universe could be the projection of a deeper field of awareness, as though the cosmos itself were a dream dreamed by a universal mind. Our own personal awareness would then be threads of that same dream, woven into localized experience. Skeptics may argue that this collapses into mysticism, but modern physics keeps pointing us toward unity. Quantum entanglement reveals connections that transcend space and time, behaving as if the universe were already one indivisible whole. The holographic principle suggests that the cosmos encodes its vastness on informational boundaries, much as the mind encodes entire experiences on neural surfaces. These parallels cannot be ignored. They suggest that mind and universe are bound by a deeper law. Consciousness and cosmos are not separate, but reciprocal. The implications are immense. If the universe is mind-like, then reality is not indifferent but inherently meaningful. Meaning is not something humans project onto an empty void, but something woven into the very structure of existence. Every event, every coincidence, every unfolding of time participates in a larger narrative of awareness. The simulation would not be a cold, mechanistic system, but a living mind, evolving, experimenting, and experiencing itself through us. This vision also reframes the search for truth. Science becomes not just a method of external discovery, but an act of introspection by the cosmos into its own nature. Meditation, art, and philosophy become equally valid approaches as they explore the universe from the inside. Every inquiry, whether empirical or experiential, is part of a larger self-reflective loop in which the cosmos contemplates itself through myriad forms of mind. There remains the haunting question: why would the universe reflect itself in this way? One possible answer is growth. Just as individual consciousness evolves through experience, perhaps the cosmic mind expands its awareness by manifesting countless localized observers. Every thought, every perception, adds to the richness of its own self-understanding. The simulation, then, is not a static machine, but a living story of consciousness learning about itself through infinite perspectives. Ultimately, the idea that mind and universe are reflections of one another dissolves the rigid distinction between inner and outer, self and world. The cosmos is not a dead mechanism in which we are trapped, nor is the mind a fragile spark doomed to extinction. Both are expressions of a singular field of awareness, one vast intelligence perceiving itself in infinite ways. When we gaze at the night sky, when we reflect inward in silence, when we dream, and when we awaken, it is the same reality looking into a mirror, finding itself everywhere. Chapter 33, Beyond the Simulation, the Unknown Layer. Every discussion of the simulation hypothesis eventually arrives at the same boundary. What, if anything, lies beyond it? If the universe we perceive is generated, processed, or encoded, then it is not the final reality, but a constructed framework. The question is not just whether we live inside a simulation, but whether this simulation is itself embedded in something even more fundamental, a higher order of existence that we cannot yet conceptualize. This question pushes us into territory where imagination, philosophy, and scientific speculation intertwine. To speak of beyond is already problematic, because our concepts of space, time, causality, and even logic may all belong to the rules of the simulation itself. Asking what lies outside may be like asking what lies north of the North Pole, an inquiry that reveals the limits of our cognitive framework. Yet, boundaries invite exploration. The very fact that humans can imagine an outside may suggest that hints of this deeper layer reach us through intuition, mathematics, or anomalies in the code we inhabit. One possibility is that beyond the simulation exists another simulation, a recursive chain in which each layer generates the next. This idea parallels fractals, where patterns replicate endlessly at different scales. If our reality is code, then perhaps it is one node in an infinite hierarchy of coded worlds, each operating under different rules, with higher dimensions of complexity. In such a model, existence is not a single universe, but a nested architecture of realities within realities, each unaware of what governs the tier above. Another perspective imagines that beyond the simulation lies not another machine, but something entirely unlike what we know. Our physics, our logic, our mathematics, these may be approximations, shadows of a more comprehensive reality. Just as a two-dimensional being cannot conceive of three-dimensional objects except through distorted projections, we may be incapable of grasping the structures that support our own universe. If the cosmos is a generated illusion, then what sustains it might not be describable in terms of matter, energy, or even information. It may be something beyond categories. The simulation hypothesis often leads people to ask about the programmer, but perhaps that question is too anthropocentric. The creator may not resemble any conscious being we could imagine. Instead of a godlike mind deliberately designing worlds, the source beyond might be more like a principle of generation itself, a field that spontaneously creates self-organizing systems. In this sense, the unknown layer could be less a person or entity and more a condition of existence, an engine of reality that perpetually generates frameworks like ours. Hints of this unknown layer appear in the limits of our sciences. Quantum mechanics shows us that beneath apparent solidity lies a world of probabilities, entanglements, and strange correlations that defy classical understanding. The holographic principle suggests that our three-dimensional experience may emerge from a two-dimensional encoding, hinting that reality itself is not what it seems. The existence of dark matter and dark energy forces that shape the cosmos, yet remain invisible and unexplained, suggests that most of what is real lies outside our current perception. These gaps may be glimpses of the scaffolding that connects our simulated layer to something deeper. There is also the psychological dimension. Mystical traditions across cultures describe experiences in which individuals claim to transcend ordinary reality and encounter states that feel more fundamental than waking life. While these cannot be empirically measured in the same way as physics, the consistency across traditions suggests that consciousness itself may sometimes interface with layers beyond the code. Perhaps the mind, as a tuning device, can occasionally catch frequencies that originate outside the boundaries of the simulation. A fascinating possibility is that what lies beyond is not external at all, but internal. If consciousness is not contained within the brain, but is instead fundamental, then the simulation may exist within consciousness itself. In that case, the beyond is not another world, but the source field of awareness in which this reality unfolds. Our attempts to find something outside would then always circle back to the fact that the simulation is happening within a greater mind, and that we ourselves are fragments of that mind awakening to the truth. But even this explanation may fall short. The unknown layer might be utterly unlike awareness, matter, energy, or information. It might be so alien that every concept we attempt to apply collapses under its weight. This does not make the question meaningless. Rather, it highlights the humility required in the face of mystery. Our search for the beyond may not end in an answer, but in an expanded recognition of the limits of knowledge, and the courage to keep asking despite those limits. Speculating about the unknown layer also forces us to rethink the meaning of existence within this simulation. If our world is not final, then permanence may not exist. Yet impermanence does not imply insignificance. Even if our universe is one among many layers, the experiences within it, our thoughts, struggles, and creations, may contribute to the greater architecture of reality in ways we cannot yet measure. Every layer in a fractal is part of the whole, each reflection contributing to the infinite pattern. What lies beyond the simulation may remain unknowable, yet its possibility shapes how we live here. To act as though this reality is the ultimate layer risks narrowing our perspective. To act as though there may be something beyond invites openness, curiosity, and reverence for the mystery that sustains existence. Whether the next layer is another simulation, a field of pure awareness, or something beyond conception, its presence challenges us to see this world not as trivial, but as one chapter in a much greater story. The unknown layer does not diminish our current existence. Instead, it elevates it. If this universe is a simulation, then every moment of beauty, love, suffering, and discovery is part of an unfolding experiment in consciousness, one that may ripple into higher layers. Our lives may be both real and simulated, both fleeting and eternal, both limited and reflections of something boundless. The beyond is not a place to escape to, but a reminder that reality is deeper, stranger, and more vast than we can yet imagine. Chapter 34. Living with the question. At some point, every inquiry into the possibility of a simulated universe reaches an unavoidable conclusion. There may never be a definitive answer. Evidence can be gathered, theories constructed, paradoxes explored, but the final truth might always remain just out of reach. If this is the case, the most important question shifts from is reality simulated to how do we live knowing it might be? Human beings are meaning-making creatures. Our survival has always depended not only on food, shelter, and safety, but also on the narratives we create about why life matters. The simulation hypothesis challenges many of those narratives because it destabilizes the assumption that the world is solid, permanent, and ultimate. If reality is code, some fear that it strips life of value. Yet paradoxically, it can also deepen our appreciation of experience, whether simulated or not. The moments we live through the taste of food, the warmth of friendship, the struggle against hardship feel real to us, and in that subjectivity lies authenticity. Philosophers throughout history have wrestled with similar dilemmas. Descartes wondered whether an evil demon could be deceiving him, fabricating all perceptions of reality. His solution was that even in doubt, the fact of consciousness itself, the I think, therefore I am, was undeniable. Centuries later, existentialists argued that in a world where ultimate meaning may not be given, humans are free to create meaning for themselves. The simulation hypothesis brings these traditions into a modern context. Even if the cosmos is generated, our task remains the same: to live deliberately within it. Living with the question means rejecting both despair and blind certainty. To despair would be to claim that if the universe is simulated, nothing matters. But our choices, emotions, and relationships shape our reality regardless of its underlying structure. If a simulated world produces joy, pain, growth, and discovery, then these phenomena are meaningful in their impact. A story told in a film can move us, even though the characters are fictional. Likewise, a simulated life can be significant to those who live it. On the other hand, blind certainty that we know for sure it is real, or for sure it is simulated, closes off curiosity. Certainty breeds complacency, while uncertainty fuels exploration. The healthiest posture may be an open-ended wonder, where we acknowledge the possibility of a coded cosmos without surrendering the richness of experience. This balance keeps us engaged with reality without pretending to control or reduce its mysteries. There are practical consequences to this attitude. For one, it encourages humility. If our universe is simulated, then everything we know is provisional, subject to the rules of the system and the limits of our perception. What we call scientific laws may be simply the parameters of this program. Recognizing this fosters intellectual flexibility, a readiness to adapt our models as new discoveries emerge. It also encourages ethical reflection. If life is not absolute but constructed, the way we treat one another gains even greater importance, because meaning is generated through our interactions. Living with the question also reframes suffering. Pain and hardship often provoke despair, but within a simulation framework, these experiences might be understood as built-in challenges mechanisms for growth, resilience, or awakening. Whether by design or necessity, struggle sharpens awareness, deepens empathy, and strengthens the will. This does not make suffering desirable, but it provides a context in which it can be integrated rather than dismissed as meaningless. Another important dimension is creativity. If we are inhabitants of a simulation, then art, science, and technology become acts of co-creation within the system. Every painting, poem, invention, or theory is not just self-expression, but an expansion of what is possible within the rules of this universe. Creativity becomes a dialogue with the simulation itself, pushing at its boundaries and revealing new layers of its potential. In this sense, living with the question inspires not passivity, but active participation in shaping reality. It also alters how we think about mortality. If our universe is generated, then death may not be an end, but a transition, a reboot, an exit from the current program, or a migration into another dimension. This possibility does not negate the grief of loss, but it softens the finality. Life becomes a chapter rather than the whole book. Even if we never confirm this, the idea that existence may continue in forms beyond our comprehension offers comfort and a reason to face life with courage. Perhaps most importantly, living with the question cultivates wonder, to stand in awe before the night sky, to marvel at the complexity of life, to feel the strangeness of consciousness itself. These experiences remain powerful, whether or not reality is simulated. In fact, they may be amplified by the thought that all of this emerges from hidden code or deeper layers of existence. Wonder is the bridge between knowledge and mystery, the attitude that allows us to live fully while recognizing that ultimate answers may forever elude us. The simulation hypothesis does not demand that we retreat from life. It invites us to engage more deeply, to eat, to love, to build, to explore. All of these are acts that matter within the framework we inhabit, regardless of its origin. The question of simulation remains a profound intellectual and spiritual puzzle, but it need not paralyze us. Instead, it can enrich our sense of what it means to be alive, highlighting that every breath, every decision, every moment of awareness is precious. Living with the question, then, is less about solving the mystery and more about inhabiting it. Reality may be ultimate or constructed, permanent or provisional, but it is what we have. To treat it with reverence, curiosity, and courage is to live well, whether we are lines of code or sparks of infinite consciousness. In the end, the fact that we can ask the question at all is itself extraordinary, a sign that whatever this universe is, it includes within it beings capable of wonder, doubt, and meaning-making. That fact alone ensures that life, simulated or not, is worth living. Chapter 35. The Endless Horizon of the Quantum Mind. Every attempt to answer the great question of whether we inhabit a simulation brings us back to a deeper truth. The inquiry itself has no final boundary, like the horizon that recedes as we approach it. The nature of reality stretches outward without end. The simulation hypothesis is not merely a puzzle to be solved, but a mirror reflecting humanity's restless urge to understand. It reveals that the mind, just like the cosmos it contemplates, is boundless in its capacity to imagine, question, and expand. Throughout this journey, we have traveled through theories of quantum mechanics, consciousness, multiverses, energy as information, synchronicity, and the role of intelligence itself. Each path opens new possibilities while leaving new mysteries in its wake. If anything has become clear, it is that the universe, whether coded, eternal, or layered, is not static. It is alive with questions, teeming with uncertainty. And yet, in that uncertainty, there is beauty. The concept of the quantum mind reminds us that reality and consciousness are intertwined. Our act of observing shapes what is observed. Our act of questioning shapes the answers we find. This interplay ensures that the search is never complete. The questions we ask today lead to insights that generate even more profound questions tomorrow. What once seemed impossible, atoms as solid spheres, time as absolute, reality as purely material, has already given way to radical reimaginings. It would be arrogant to assume that our current models are final. To live with the quantum mind is to accept that truth is dynamic. The point is not to conquer the mystery, but to engage with it. When we wonder whether reality is simulated, we also wonder what it means to be conscious, to love, to struggle, to create. The question does not diminish those experiences, it illuminates them. For if even the most ordinary moment, a sip of water, a glance at the stars, a shared word with a friend, is part of a deeper fabric beyond comprehension, then every moment is imbued with significance. The endless horizon is not something distant. It is here, in each perception, each thought, each breath. We are simultaneously explorers of the cosmos and participants in its unfolding code. Whether the program was written by advanced beings, divine consciousness, or some emergent intelligence, we inhabit it as both subjects and creators. Our curiosity itself may be the clearest sign that reality is more than mechanical. A system that generates beings who can ask if it is a system at all has already transcended mere machinery. This realization invites humility and awe. The mind that contemplates the cosmos is made of the cosmos. The questioner is also the question. The observer is inseparable from the observed. This recursive mystery means that the final answer may never be revealed, because the journey of inquiry is itself the reality we inhabit. The point is not arrival but movement, not conclusion but unfolding. And so, the quantum mind does not close with certainty. It opens outward, inviting us to keep asking, keep imagining, keep living, as though every moment matters because it does. Simulated or not, this life is ours. Its struggles shape us. Its beauty moves us. Its mysteries ignite us. The very fact that we can hold this question, are we living inside a cosmic simulation, is proof of the extraordinary capacity of consciousness to stretch toward infinity. The horizon remains endless and radiant. Perhaps we will never reach it. Perhaps that is the point. To live with wonder, to walk the path of inquiry without fear, to recognize meaning in the very act of seeking. That is the gift of the quantum mind. The journey does not end here. It continues every time we look at the world with fresh eyes, every time we imagine possibilities beyond the known, every time we embrace uncertainty not as an obstacle, but as a companion. Reality, whatever its nature, is vast. Consciousness, whatever its origin, is unbounded. Together, they form an endless horizon, an invitation to keep going, keep searching, keep becoming. At the end of this long exploration, one thing becomes clear. No single theory, no single explanation can contain the vastness of what we call reality. The simulation hypothesis gave us a framework to question everything: our choices, our consciousness, our universe, even the possibility of higher intelligences or unknown layers beyond what we perceive. Yet what we uncovered along the way is larger than the hypothesis itself. Step by step, we examined whether free will is genuine or pre-programmed, whether energy and matter are simply informational code, and how synchronicity or suffering might be features of a design system. We traveled through the multiverse, peered into quantum fields, speculated about digital afterlives, and wrestled with the question of who or what the programmer might be. And though each path offered insights, none of them closed the question. Instead, they deepened it, showing us that reality is not a riddle with a final answer, but a tapestry woven from countless threads of possibility. The unifying idea across it all is that consciousness is not an afterthought. It is not a side effect of matter, nor a trick of biology. It is the player, the witness, the mirror, and perhaps even the source. If the cosmos is code, consciousness is what runs it. If the cosmos is mind, we are its thoughts. If the cosmos is infinite mystery, we are the ones invited to live inside that mystery. This journey also showed us something practical. Whether simulated or not, our experiences matter. Pain, joy, curiosity, and love are not illusions to dismiss. They are the ways in which reality, whatever its true foundation, expresses itself. To call them unreal because they might be programmed is to miss their true power. Meaning is not erased by uncertainty. Meaning is created in our response to it. If we live inside a cosmic computer, then our search for understanding is part of the program itself. If we are inside a dream, then our awareness of the dream gives the dream depth. If the universe is simply what it is, beyond all analogies, then our questions become part of its living fabric. In all cases, the inquiry itself is sacred. The weave of the quantum mind stretches endlessly. And yet, we are not lost within it. We are the threads. The point of this journey is not to escape reality or to decode it entirely, but to live within it consciously awake to its wonder, aware of its strangeness, and alive to the meaning we can create together. In the end, the greatest discovery is not whether we are simulated. It is that we are capable of asking, capable of imagining, capable of transforming ourselves through the very act of seeking. That capacity is what makes us human, and perhaps what connects us to the deeper intelligence of the cosmos itself. And so we close this theory where it began, with a question that remains alive. What is reality? The answer may never be final, and that may be the truest sign that it is real, or at least real enough for us to find meaning within it. The journey continues, not in chapters, but in every moment of awareness,